Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're drifting away from Earth, past the familiar planets, past Mars with its dusty red deserts, past Jupiter with its storms and stripes, and far beyond the comfortable neighbourhood of our solar system, to visit a world so extreme that it sounds at first like someone made it up during a very dramatic weather report. A planet where the dayside is so hot that metals can turn into vapour. A planet where powerful winds may carry that vapour around the globe. A planet where, on the cooler night side, iron may condense and fall from the sky. Not rain made of water, not snow made of ice, not the gentle drizzle you might hear against a window while you're trying to fall asleep, but rain made from metal. Iron rain, falling through the darkness of an alien night. The world is called WASP-76b, which is not the most soothing name ever given to a place in the universe. It sounds a little like a password you forgot to write down, or a small household appliance with a manual no one can find. But behind that sharp catalogue name is one of the most fascinating planets astronomers have ever studied. It is not a rocky world like Earth. It is not a calm blue marble with oceans and clouds and soft weather drifting over continents. WASP-76b is a giant planet, swollen and hot, orbiting so close to its star that a year there lasts less than 2 Earth days. Imagine celebrating your birthday every couple of days. Charming at first, perhaps, until you realise the cake would probably melt before anyone could light the candles. This is a kind of world astronomers call an ultra-hot Jupiter. That phrase already tells us quite a bit. It is giant like Jupiter, but unlike Jupiter, which lives far from the Sun in the cold outer solar system, WASP-76b circles its star at a distance that would make our inner planet seem relaxed by comparison. It is pressed close to the light, held in a tight orbit, constantly blasted by radiation from its parent star. In our own solar system, Mercury is the planet closest to the Sun, and even Mercury seems almost leisurely when compared with a world like this. WASP-76b is not simply warm. It is not merely hot. It is hot in a way that changes what an atmosphere can be. Heat there is not just a temperature on a thermometer. It is an active force, pulling molecules apart, lifting metals into the air and turning weather into something strange enough to make Earth's storms look very polite. Before we go too far into this metal-raining sky, let me ask you something gently, wherever you are right now. What is the weather like outside your window? Is it raining where you are, or is the night clear? Are you listening from a quiet room, a busy city, a bed with the lights turned low, or maybe somewhere where the world is just beginning to wake up? It is a funny thing to think about weather while we talk about a planet so far away. Here on Earth, weather is part of everyday life. We complain about it, dress for it, make small talk about it, and sometimes let it decide our mood for the whole morning. A little rain can make a street shine. A cold wind can make you walk faster. A warm afternoon can make everything feel slower. Weather feels ordinary because we live inside it. But the deeper we look into the universe, the more we discover that weather is not always gentle, familiar, or even made of the ingredients we expect. Some worlds have clouds of silicate dust, tiny grains that are more like sand than mist. Some may have storms of glassy particles blown sideways by violent winds. Some have atmospheres so hot that the chemistry of the air begins to resemble the inside of a furnace. And then there is WASP-76b, where the idea of rain becomes almost difficult to picture, because what falls from the sky may once have been iron vapour glowing in the heat of an endless day. If that sounds strange, it should. The universe has a habit of taking ordinary words, rain, wind, clouds, seasons, and stretching them until they become wonderfully unfamiliar. If you find this kind of journey soothing, or if you like having the universe explained softly enough that your thoughts can loosen their grip on the day, I would be ever so grateful if you gave the video a like, maybe subscribed, and joined this quiet little corner of science again. It helps these calm space stories reach other tired minds, other curious night owls, and perhaps the occasional person who clicked because they saw the words Iron Rain and thought, quite reasonably, "Excuse me, what?" And I do hope this is interesting without being too exciting. That is always the delicate balance here. We're exploring a planet where metal may fall from the sky, but we're doing it at a pace suitable for blankets, soft breathing, and not checking the clock every few minutes. So settle in, let your shoulders drop a little if they have been holding the day too tightly, and imagine Earth fading behind us. Not disappearing in a frightening way, but shrinking gently into the background, like a lamp seen from the far end of a street. We leave behind the blue of oceans, the white curl of clouds, the green and brown patchwork of land. We move outward through the dark, past the moon, past the planets, past the familiar paths we learned about in school, and then beyond them into the wider galaxy where stars are not just points of light but homes to other worlds. Some of those worlds are small and rocky, some are cold and distant, some are so close to their stars that they seem less like planets and more like experiments in what matter can endure. WASP-76b belongs to that last group. It is not a place a spacecraft could casually land. There is no solid surface waiting beneath a gentle atmosphere, no hills, no lakes, no beach, no quiet valley where an explorer might set down a flag and take a careful first step. It is a gas giant, so what we call the planet is mostly atmosphere, pressure, heat, and depth. If you could somehow descend into it, which is not recommended even by very adventurous travel agents, there would be no firm ground to meet your feet. You would move downward through layers of gas growing thicker and hotter, into pressures that would crush ordinary machines and temperatures that would make ordinary materials give up immediately. On WASP-76b, the sky is not a calm covering over a world. The sky is the world, and that sky is divided in a way that feels almost theatrical. Because WASP-76b orbits so close to its star, it is believed to be tidally locked. That means the same side of the planet always faces the star, while the opposite side always faces away. The moon does something similar with Earth. We always see roughly the same face of the moon because its rotation and orbit are synchronized. But on the moon, that arrangement gives us a familiar near side and far side. On WASP-76b, it creates something far more extreme, a permanent dayside and a permanent nightside. One half of the planet is always staring into the furnace of its star. The other half is always turned towards space. Try to picture that for a moment. No sunrise sweeping slowly over the horizon, no sunset cooling the ground, no morning that arrives after a long night, no evening that softens the end of a day. Just one hemisphere locked in constant light and the other kept in endless dark. Earth's weather is powered by change, day into night, warm regions and cold regions, oceans and continents, seasons and storms. WASP-76b has changed too, but it is arranged around a permanent contrast. On one side, heat pours down without pause. On the other, temperatures are lower, though lower is a very Earth-centered word here. The night side of WASP-76b is still far hotter than almost anything we experience naturally on our planet. It is not cold in the way we understand cold. It is only cool compared with the day side. The way an oven that has been turned down is cooler than a blast furnace. That difference matters because chemistry pays close attention to temperature. On the day side, the heat can be so intense that iron is thought to exist as vapor in the atmosphere. This is where the story becomes strange in a very concrete way. Iron, the material in bridges, tools, pans, nails, machines, and the core of our own planet, may be lifted into the air as a gas. Here on Earth, iron feels solid, heavy, stubborn. You can hold an iron object and feel that it has weight. You do not expect it to float through the sky. You do not expect it to behave like humidity. But WASP-76b is not asking what we expect. It is following physics under conditions so extreme that the familiar categories begin to loosen. The star heats the dayside. The atmosphere responds. Winds rush from the overheated dayside toward the darker nightside, trying in their own wild way to move energy around the planet. These winds are not breezes that stir curtains. They may race at tremendous speeds, carrying heat and chemical material with them. Among that material may be iron vapor. As the air crosses into the nightside, the temperature drops enough for the iron to condense. Condensation is a word we know from ordinary life. Warm, moist air touches a cold window and droplets appear. Steam rises from a cup of tea, meets cooler air, and turns into visible mist. On Earth, this process gives us dew, fog, clouds, and rain. On WASP-76b, the same broad idea may involve metal. Iron vapor cools. Iron gathers into droplets or particles, and then, somewhere in that alien darkness, it falls. It is tempting to imagine this as heavy droplets of glowing metal splashing through a night sky, and perhaps some version of that image is not too far from the emotional truth. But we should be careful and kind to the science here. Astronomers have not stood beneath the clouds of WASP-76b holding a very unfortunate umbrella. They have not filmed iron raindrops falling in slow motion. What they have done is even more delicate. They have studied the light of the planet's star as it passes through the edge of the planet's atmosphere during a transit. When WASP-76b moves in front of its star from our point of view, a little bit of starlight filters through the planet's upper atmosphere before reaching us. That light carries fingerprints. Certain atoms and molecules absorb certain colours, leaving patterns in the spectrum. By reading those patterns, scientists can infer what is present in the air of a world they cannot see directly. That is one of the quiet miracles of modern astronomy. We cannot visit WASP-76b. We cannot touch its clouds or sample its winds. It is hundreds of light years away, far beyond any journey we could currently make. And yet, by catching starlight and spreading it into a spectrum, astronomers can begin to learn what its atmosphere contains, how it moves, and how different one side may be from another. There is something almost humble about that. The planet does not send us a postcard. It does not announce its weather. It simply passes in front of its star, and for a few hours some of that starlight slips through its atmosphere. Inside that faint signal, with enough patience and careful instruments, there is a story. The story that emerged was not just that iron was present. Iron had already been detected in the atmospheres of some ultra-hot giant planets. The unusual part was that the signal appeared uneven, stronger in one region and missing where scientists expected to see it, if the iron simply remained vapor all the way around. One explanation is that iron vapor is carried from the dayside toward the nightside, then condenses out of the atmosphere before it can appear again at the morning edge of the planet. In plain bedtime language, the iron goes up on the hot side, travels around, cools down, and rains out in the dark. A metal weather cycle, not powered by oceans and clouds as on Earth, but by heat, wind, and the chemistry of an atmosphere pushed to extremes. This is why WASP-76b has become one of those exoplanets that captures the imagination immediately. Many discoveries in astronomy require a little patience before their wonder becomes obvious. A small dip in starlight, a subtle wobble of a star, a spectral line shifted by a tiny amount. These are beautiful clues, but they can sound modest at first. WASP-76b, however, arrives with a phrase that opens the door all by itself, the planet where it rains iron. It is simple, strange, and unforgettable. It tells us at once that other worlds are not just copies of ours with different colours. They can be places where the rules of ordinary experience are rearranged. They can be planets where familiar materials enter unfamiliar roles. Iron is no longer just something inside a planet or forged in stars or built into human tools. It becomes weather. And yet, there is also something connecting this extreme world to Earth. Not because Earth has iron rain, thankfully, but because the same basic physical ideas apply. Heat moves, air circulates, materials change form when temperature and pressure change. Light carries information, gravity keeps planets bound to stars, chemistry responds to conditions. The universe is not random nonsense. Even in its strangest places, it is following patterns. WASP-76b may seem outrageous, but it is not magic. It is physics allowed to run under conditions we do not have at home. That is often where science becomes most interesting. It takes a familiar rule and places it somewhere unfamiliar, then shows us what the rule can do. Think about water on Earth. It can be solid ice, liquid rain, floating vapor, soft snow, heavy hail, morning dew, high clouds, mist over a field, or frost on a window. The same substance changes its behavior depending on the conditions around it. We're used to that because we live with water all the time. On WASP-76b, iron may have its own version of this story. In one region, it is vapor. In another, it condenses. Under different temperatures and pressures, it may form clouds or droplets, or settle deeper into the atmosphere. The material is different, the world is different, and the scale is far more extreme, but the principle is not entirely alien. The universe keeps teaching us by changing the ingredients. It is also worth pausing with the name itself, WASP-76b. The WASP part comes from the Wide-Angle Search for Planets, a project designed to find exoplanets by looking for tiny dips in starlight when planets pass in front of their stars. The number refers to the star system in the catalogue, and the little b means it was the first planet found orbiting that star. In exoplanet naming, the star itself is usually considered A, even if we do not say it that way, and the planets begin with B. It may not sound romantic, but it is practical. The galaxy is crowded. There are thousands of known exoplanets now and many more waiting to be confirmed, so astronomers need names that can keep the shelves tidy. Still, behind each tidy label may be a world of storms, heat, chemistry, and surprise. WASP-76b was first announced in 2016, and since then it has become a valuable target for studying the atmospheres of ultra-hot giants. Part of the reason is that it is large and puffy, with an atmosphere that can leave a stronger imprint on starlight. A bigger atmospheric signal gives astronomers more to work with. It is a little like trying to hear a whisper in a quiet room rather than in a crowded train station. The star is bright enough, the planet is close enough to its star, and the atmosphere is extended enough that careful instruments can pull out details. Not easy details, of course. This is astronomy, where even a generous clue often arrives wrapped in noise, calibration, and months of analysis. But possible details. And possible is a powerful word in science. The more we study planets like WASP-76b, the more we learn that the category planet is much broader than our solar system once suggested. For a long time, the planets we knew best followed a familiar arrangement. Small rocky worlds close to the sun, gas giants farther out, ice giants beyond them. Then, in the 1990s, astronomers began finding planets around other stars, and the neatness of our local example did not survive for very long. There were giant planets orbiting scorchingly close to their stars, planets larger than Jupiter moving around their suns in only a few days, planets with strange densities, odd orbits, extreme temperatures. Nature, it turned out, had been making worlds in a much wider range of styles than our solar system had shown us. Hot Jupiters were among the first great surprises. They are giant planets in very tight orbits, and they raised immediate questions. Did they form close to their stars, or did they form farther out and migrate inward? How do their atmospheres survive such intense radiation? What happens to clouds, winds, magnetic fields, and chemistry when a giant planet is roasted from one side? WASP-76b is part of this larger investigation. It is not just a curiosity with dramatic weather, It is a clue to how giant planets behave when placed in extreme conditions. It helps scientists test models of atmospheric circulation, heat transport, chemical condensation, and planetary evolution. The iron rain is the memorable part, but behind it is a deeper question. How does a planet respond when its star overwhelms it? For us, from our safe little distance, WASP-76b is also a reminder of how gentle Earth is. That does not mean Earth is always gentle to us. Earth has hurricanes, droughts, volcanoes, floods, heat waves, blizzards, and all sorts of moods. But compared with an ultra-hot giant planet locked beside its star, Earth is astonishingly balanced. Our rain is liquid water. Our winds are mostly survivable. Our nights cool the land. Our days return on a steady rhythm. Our atmosphere is thin enough to see through and thick enough to breathe. We live on a world where weather can be inconvenient, beautiful, frightening, boring, and life-giving all at once. WASP-76b shows us weather as a cosmic idea, not limited to our comfort zone. It makes Earth feel both smaller and more precious. So tonight, as we begin this slow journey into the iron weather of a faraway planet, we are not only asking what WASP-76b is like, we're asking how a world becomes so extreme. We're asking how astronomers discovered it, how they measured a planet so distant, how a gas giant ends up so close to its star, and what happens to an atmosphere when one side is baked forever, while the other never sees daylight. We're asking how iron, a material we normally associate with strength and solidity, can become part of an alien sky. We're asking what rain means when the universe is allowed to choose a different recipe. And there is a quiet comfort in that kind of question. Not because the planet itself is comforting, I would not recommend it for a weekend retreat, but because understanding it gives shape to the strangeness. The universe becomes a little less like a collection of distant lights and a little more like a place filled with processes, stories, and worlds doing what worlds do. Some worlds freeze in darkness, some burn close to their stars, some hide oceans under ice, some carry storms wider than Earth, and one, far away around a bright star, may send iron falling through its night. For now, keep that image gently in mind. A giant planet close to its sun. One side glowing under constant heat. One side turned away into permanent darkness. Winds moving between them. Metal rising, travelling, cooling and falling. A weather cycle made not for life as we know it. Not for oceans or forests or open windows on a rainy evening. But for a world that teaches us how varied planets can be. And before we follow the iron deeper into the atmosphere, before we stand at the edge of that discovery and ask how anyone found such a place at all, we should begin with the first clue. The tiny dimming of a star, the patient watching of the sky, and the strange moment when a distant point of light revealed that something enormous was passing in front of it. That first clue, the tiny dimming of a star, sounds almost too small to matter. A point of light in the sky shines steadily, night after night, and then, for a short while, it becomes just a little less bright. Not dramatically. Not as if someone switched off a lamp. More like the faintest blink, the smallest lowering of a candle flame, the kind of change you would never notice with ordinary eyes while standing in a garden and looking upward. And yet, hidden inside that slight fading was a planet. Not a small one, not a quiet one, not a distant icy pebble moving slowly in the dark, but a giant world racing around its star so closely that its entire year could pass during a long weekend on Earth. This is one of the beautiful things about astronomy. Sometimes the universe announces a new world not with a picture, not with a dramatic flash, but with a dip in starlight so modest that it needs patient instruments, careful mathematics, and people willing to ask, did that star just blink? WASP-76b was found using the transit method, which is one of the most successful ways astronomers discover planets around other stars. The idea is simple enough to explain while half asleep, which is always appreciated. If a planet passes in front of its star from our point of view, it blocks a tiny portion of the star's light. The star appears to dim, then brightens again once the planet moves out of the way. If the same dimming happens again and again at regular intervals, astronomers can begin to suspect that something is orbiting the star. It is a bit like noticing a moth crossing in front of a porch light, except the porch light is a star hundreds of light years away, the moth is a planet larger than Jupiter, and the porch is the entire galaxy. So, perhaps not exactly like a moth and porch light, but close enough for a sleepy comparison. The word wasp in WASP-76b does not refer to the insect, though it is easy to picture a little cosmic wasp buzzing around a star. It comes from the wide-angle search for planets, often called the WASP survey or super WASP. This project used wide-field cameras to watch huge numbers of stars at once, looking for those tiny repeating dips. It was not trying to take beautiful close-up portraits of planets. It was doing something more patient and statistical. It watched the sky and waited for stars to tell on themselves. Night after night, the cameras gathered brightness measurements from thousands upon thousands of stars, building long records called light curves. A light curve is simply a record of how bright something appears over time. Most stars vary a little. Some pulse, some flare, some have spots that rotate in and out of view. And every now and then, one of them dims in a way that says very quietly, "Something just passed in front of me." Of course, a dip in starlight does not automatically mean a planet has been found. The universe is wonderful, but it is also very good at making scientists check their work. A dimming star could be part of an eclipsing binary system, where one star passes in front of another. It could be blended with light from a nearby star. It could be affected by instrumental noise, atmospheric conditions, or some other very unglamorous problem that makes a graph look more exciting than it really is. This is why discovery is not a single moment where someone sees a dip and immediately declares a new world. It is more like a careful conversation with the data. First comes suspicion, then comes checking, then more checking, then follow-up observations. Then, if the evidence holds together, a planet earns its place in the catalogue. For WASP-76b, the repeating transit signal suggested a large planet moving very close to its star. The dips came at regular intervals, revealing an orbit of about 1.8 Earth days. That is astonishingly short. Mercury, the closest planet to our Sun, takes 88 Earth days to complete one orbit. Earth takes 365 days. Jupiter takes almost 12 Earth years. WASP-76b goes around its star in less time than it takes many people to recover from a slightly ambitious weekend. If you lived by its calendar, Monday morning would arrive with alarming enthusiasm. But that short orbit was also part of what made the signal easier to notice. A planet that transits every few days gives astronomers repeated chances to see it. A planet like Jupiter, orbiting far from its star, might only transit once every many years if viewed from the right angle. WASP-76b kept passing in front of its star again and again, like a very punctual shadow. Still, transit data alone mainly tells astronomers that something is crossing the face of a star. It can reveal the planet's size because the larger the planet, the more light it blocks. If a huge planet crosses in front of a star, the dip is deeper than it would be for a small rocky planet, but size is not enough. To understand whether the object is truly a planet and not a faint star or something stranger, astronomers often need radial velocity measurements. This is another elegant trick. A planet does not simply orbit its star while the star sits perfectly still. Both objects orbit their shared centre of mass. Because the star is far heavier, it only wobbles a little, but that little wobble can be detected in the star's light. As the star moves slightly toward us and away from us, its spectral lines shift a tiny bit, like the pitch of an ambulance siren changing as it passes by, only quieter, slower, and with fewer people trying to cross the road. By measuring that stellar wobble, astronomers can estimate the mass of the planet. This matters because a large object with the mass of a star is not a planet, no matter how politely it transits. WASP-76b turned out to have a mass close to Jupiter's, but a much larger radius. In other words, it is a gas giant, but an inflated one. It is puffed up, swollen by the intense heat of its nearby star. Imagine a balloon held too close to a heater, though please do not try that as a home demonstration. The planet's atmosphere is expanded, giving it a larger silhouette as it crosses the star. That expanded atmosphere would later become very useful, because it makes the planet easier to study during transits. More atmosphere means more starlight filtering through it. More filtered starlight means more clues. The original discovery did not immediately begin with iron rain. That came later, after better instruments and more detailed observations turned the planet from a dot in a catalogue into a place with weather. This is important because scientific discovery often unfolds in layers. The first layer is, there is a planet here. The second layer is, here is how big it is, how massive it is, and how it moves. Then, if the target is favourable and the instruments are good enough, comes the more delicate question. What is its atmosphere doing? That is when a distant planet begins to feel less like a number and more like a world. WASP-76b was already interesting because it belonged to the class of hot Jupiters, and even more specifically ultra-hot giants. Hot Jupiters changed planetary science when they were first discovered because they were not supposed to be where they were, at least not according to the tidy expectations many people had from our own solar system. Jupiter sits far from the Sun, beyond the asteroid belt, in a region where cold materials could help build a giant planet. A gas giant close to a star seemed surprising. How could such a massive planet form there? Did it form farther away and migrate inward? Did interactions with a disk of gas or with other planets drag it into a tight orbit? These questions are still part of exoplanet science, and every hot Jupiter adds another example for astronomers to compare. WASP-76b is extreme even among these close-in giants. It orbits at only about 0.033 astronomical units from its star, which means it is far closer to its star than Mercury is to the Sun. An astronomical unit is the average distance between Earth and the Sun, so 0.033 astronomical units is a tiny fraction of that. It is close enough that the star dominates the planet's environment. The dayside is blasted by radiation. The atmosphere is heated and expanded. The orbit is so tight that tidal forces are expected to lock the planet's rotation, keeping one side permanently facing the star. This means the planet's discovery was not just the discovery of another distant giant. It was the discovery of a natural laboratory where heat, gravity, radiation, and atmospheric motion all operate at the edge of what planetary weather can be. The star itself, WASP-76, is an F-type star, hotter and brighter than our Sun. That matters too because a planet so close to a brighter star receives an enormous amount of energy. If Earth were moved too close to the Sun, our oceans would boil and our atmosphere would change beyond recognition. WASP-76b has no oceans to lose in the familiar sense, no forest to dry, no surface farms to worry about. It is a giant atmosphere wrapped around a deep planetary interior. But that atmosphere still responds strongly to the star. The incoming energy shapes its temperature, its circulation, its chemistry, and eventually the strange possibility of metal rain. Now, let us slow down with the discovery process itself, because there is something comforting about the patience involved. It is easy to imagine astronomy as a series of sudden revelations. A telescope points, an image appears, and there it is. But many exoplanets are discovered more like a careful heartbeat heard through a wall. A survey telescope watches a field of stars. Software looks for patterns. Human researchers examine the candidates. Other telescopes follow up. Measurements are repeated. False positives are ruled out. The planet is not seen directly. Instead, its presence is inferred from what it does to the light of its star. It blocks a little light. It pulls the star slightly. It repeats its movement with clock-like regularity. Slowly, the invisible becomes measurable. There is also something very human about the naming system, even if it seems dry at first. WASP-76b sounds cold and technical, but that name carries the trail of its discovery. WASP tells us the survey that found it. The number points to the star system. The lowercase b marks the first confirmed planet orbiting that star. If another planet were found in the system, it would likely become WASP-76c. Not very dramatic, perhaps, but useful. The galaxy has no obligation to keep its planets in a small, memorable list. Astronomers need a filing system, and the filing system has to handle thousands of worlds, many of which refuse to be simple. Somewhere behind each catalogue name is a real planet, or at least as real as any world can be when we know it through starlight, gravity, and patient inference. Once WASP-76b was known, astronomers had a target worth revisiting. This is another important part of the story. Discovery is not the end, it is the invitation. A confirmed exoplanet becomes a place scientists can return to with better instruments, different wavelengths, and sharper questions. They can ask whether its atmosphere contains water vapour, sodium, metals, molecules, clouds, or hazes. They can compare transit observations with eclipse observations, when the planet passes behind the star and its own glow is temporarily hidden. They can search for heat patterns, wind speeds, and chemical differences from one side to the other. A planet first found by a dip in light becomes, over time, a whole puzzle. The iron rain idea came from this later stage, when astronomers used the espresso instrument on the Very Large Telescope in Chile to study the planet's atmosphere in high detail. Espresso is a spectrograph, which means it separates light into its component colours with extreme precision. If the word spectrograph sounds like something that belongs in a very serious laboratory, that is because it does, but the basic idea is familiar. A prism spreads white light into a rainbow. A spectrograph does something similar, but with enough accuracy to reveal fine, dark and bright features, the fingerprints of atoms and molecules. Every chemical element absorbs and emits light at particular wavelengths, so when starlight passes through a planet's atmosphere, the atmosphere removes tiny portions of that light. Scientists can look at the missing pieces and identify what was in the way. During a transit, the planet's atmosphere forms a thin ring around the dark disk of the planet. Starlight passing through that ring is filtered by the gases there. For a world like Earth, such a technique might reveal oxygen, water vapour, carbon dioxide, or methane if seen from far away with the right instruments. For WASP-76b, the atmosphere is far hotter and stranger. Instead of looking for signs of habitability, scientists were looking for the chemistry of an extreme gas giant. Iron was one of the key signatures. The surprising part was not only that iron vapour appeared, but that its signal changed around the planet's limb, the border region seen during transit. Iron was detected strongly on the evening side where gas moves from the day side toward the night side, but it was not seen in the same way on the morning side where material would be expected to emerge after passing through the night side. That missing iron became the clue. If iron vapour is present on the hot day side and carried by winds into the night side, then on the cooler night side it may condense. Once it condenses, it is no longer floating as vapour in the same way, so the morning side does not show the same signal. The atmosphere has changed the iron's form. It has rained out, or at least condensed out of the upper atmosphere. The phrase, "it rains iron," is dramatic, but it is not empty drama. It is a shorthand for a real physical process, vaporized iron transported by atmospheric winds into cooler regions where it condenses and falls. There is a lovely strangeness in how indirect this is. Nobody watched a storm cloud form over WASP-76b. Nobody measured iron droplets with a probe. The planet is too far away for that. Instead, astronomers read the absence of a signal. They saw where iron appeared, noticed where it did not, and built an explanation using temperature, circulation and chemistry. Science often works this way. A missing footprint can tell you which way someone walked. A silence can tell you what note should have been played. A planet's atmosphere can reveal its weather not only by what is present, but by what has disappeared. This is where the discovery becomes almost like detective work, though with fewer magnifying glasses and more high-resolution spectroscopy. The first detective clue was the transit. Something big passes in front of the star every 1.8 days. The second was the wobble. The star moves in a way consistent with a giant planet. The third was the planet's size and orbit. It is a hot, inflated gas giant very close to its star. The fourth was atmospheric. Iron vapor appears in a pattern that suggests different chemistry between day and night. Each clue by itself is interesting. Together they build the picture of a world with an atmosphere in motion, a world where one hemisphere is heated enough to vaporize metals and the other allows those metals to condense. It is worth appreciating how much astronomy depends on repetition. WASP-76b's orbit is short, so its transits happen often. That gives observers repeated opportunities to study the same event. Each transit is like another page of the same book. One page may be noisy, another may have better conditions, another may be observed with a different instrument. Over time, the pages begin to make sense together. A single dip in light is not enough. A single spectrum may not settle the question, but repeated patterns, gathered carefully, begin to form a reliable story. For a sleepy mind, it may help to imagine the star as a distant lantern, and the planet as a dark bead sliding regularly across it. Every 1.8 days, from Earth's perspective, the bead crosses the lantern. Most of the light still reaches us. Only a tiny fraction is blocked. Around the edge of the bead, the atmosphere glows not with its own visible brightness, but with information. The starlight passes through that rim and arrives changed. Here is iron, here is heat, here is motion, here is a difference between evening and morning. The telescope does not see rain, but it sees enough to suspect the weather. And what a different kind of discovery this is compared with the way humanity first knew planets. Mercury, Venus, Mars, Jupiter, and Saturn were visible to ancient observers because they moved against the background stars. They were wandering lights, bright enough to be seen by eye. Uranus and Neptune required telescopes and careful observation. Pluto, later reclassified as a dwarf planet, appeared as a tiny moving point in photographic plates. Exoplanets required still another leap. Most are not seen as points at all. They are found through effects: a star dimming, a star wobbling, a lensing event, a direct image in rare cases, a timing variation, a subtle pattern. We have gone from watching wandering lights with naked eyes to noticing tiny brightness changes in stars hundreds of light years away. That is a remarkable expansion of human attention. The discovery of WASP-76b also reminds us that a planet can be scientifically important long before it becomes famous. At first, it was one of several hot Jupiters announced together, part of the growing population of close-in gas giants. Its basic properties were enough to interest specialists: short orbit, inflated radius, strong irradiation, a bright enough host star for follow-up. But the public imagination tends to wake up when a planet gains a vivid identity. A planet where it rains iron is easier to remember than a planet with a particular radius and orbital period, even though those numbers are what make the weather explanation possible. The drama rests on the data. The phrase rests on the measurements. There is a gentle lesson in that. Wonder and precision are not enemies. The beautiful sentence, "It rains iron there," depends on the less glamorous sentence. The iron absorption signal is asymmetric across the transit. The first sentence opens the imagination. The second sentence keeps the imagination honest. In good science, they belong together. One lets us feel the strangeness. The other tells us why we're allowed to believe it. So, When we say WASP-76b was discovered, we are really talking about more than one discovery. The planet was discovered as a transiting giant in a tight orbit. Then its atmosphere was explored. Then its chemistry revealed a day-night contrast. Then the possibility of iron rain turned that contrast into a story we could picture. Each stage added depth. First there was a shadow. Then there was a mass. Then there was a bloated gas giant. Then there was an alien sky. And all of it began with light, slightly reduced for a little while, returning again and again with the same rhythm. To understand why WASP-76b became such a strange world, we have to begin with where it lives. Not just the name of its star, not just its place in a catalogue, but its actual position in relation to the light that rules it. Planets are shaped by distance. Move a world a little closer to its star and its temperature rises. Move it farther away and gases freeze, clouds change, sunlight weakens, and the whole character of the planet can shift. Earth sits in a mild enough region that water can fall as rain, gather into oceans, freeze into ice, and rise again as vapour. Jupiter sits much farther out, where sunlight is weaker, temperatures are lower, and its great storms churn beneath pale, cold sunlight. WASP-76b, though, does something that would make Jupiter look like it is keeping a sensible distance. It circles its star at a distance of only about 0.033 astronomical units. That means it is only a tiny fraction of Earth's distance from the Sun, held so close to its star that its orbit is not a grand slow sweep through space, but a tight, fast loop around a furnace. A year on WASP-76b lasts about 1.8 Earth days, less than 2 days, shorter than a weekend. You could start a Friday evening on Earth, make some tea, fall asleep, wake up, go through Saturday, perhaps spend Sunday pretending not to think about Monday, and by the time the weekend was almost over, WASP-76b would have already completed more than one entire trip around its star. That is what a year means there. Not seasons changing, not months gathering, not a slow trip through the calendar, but a rapid orbit again and again around a star that fills its sky with relentless light. It is a funny thought at first, because we are so used to a year meaning something long. Birthdays, holidays, school years, work years, anniversaries, the slow turning of seasons. On WASP-76b, a year is shorter than the time many people need to decide what to watch on a streaming service. But that short year is not just a cute astronomical detail. It tells us something important about the planet's life. A planet with such a short orbit must be extremely close to its star. Gravity is pulling it around at high speed, and the star's radiation is pouring into its atmosphere with enormous intensity. In our solar system, Mercury is already close enough to the Sun that its dayside becomes brutally hot. But Mercury still orbits much farther from the Sun than WASP-76b orbits from its own star, and WASP-76b is not circling a faint little ember. Its host is an F-type star, hotter and brighter than our Sun. So the planet is not only close, it is close to a powerful source of light and heat. That combination turns an ordinary gas giant into something far more extreme. This is why astronomers call WASP-76b an ultra-hot Jupiter. The Jupiter part means it is a giant planet made mostly of gas, with a mass in the broad neighbourhood of Jupiter's mass. It is not rocky like Earth, not solid in the everyday sense, not a place with a crust where you could imagine mountains, rivers or footprints. The hot part means it orbits close to its star, much closer than Jupiter does, and the ultra part is not there for decoration. It means the heating is so intense that the atmosphere begins to behave in ways that cooler planets never experience. Molecules can break apart. Metals can exist as vapour. The difference between the star-facing side and the night side can become so large that the planet develops a kind of permanent atmospheric argument, with one half being blasted by light and the other half trying to cool in darkness. It helps to compare WASP-76b with Jupiter for a moment. Jupiter in our solar system is enormous, more massive than all the other planets combined. It has thick bands of cloud, a great red spot wider than Earth, and deep layers of hydrogen and helium. But Jupiter is far from the Sun, so its weather is shaped by its own internal heat as well as by weak sunlight. WASP-76b is a giant too, but it has been moved inward until it is almost hugging its star. If Jupiter is a massive, cold, stormy world sitting in the outer dark like a quiet old king, WASP-76b is what happens when a giant planet is placed under a stellar heat lamp and left there without mercy. The result is not simply Jupiter with a tan, it is a planet transformed. One of the most noticeable results is that WASP-76b is inflated. Its radius is much larger than Jupiter's, even though its mass is not much greater. That means the planet is puffed up, less compact than Jupiter, with an atmosphere expanded by heat. Heat gives gas particles more energy. They move faster, push outward, and make the upper atmosphere stretch farther into space. Imagine a loaf of bread rising in an oven, though this is not a very relaxing oven, and the loaf is a gas giant orbiting a star every 1.8 days. The comparison is imperfect, but the idea is useful. Energy goes in. The planet swells. The atmosphere becomes large and extended, which also makes it easier for astronomers to study when starlight passes through it during a transit. Being close to a star also changes the orbit itself over time. A planet like WASP-76b is under strong tidal forces. Tides happen because gravity pulls more strongly on the side of an object closer to the source of gravity than on the far side. On Earth, the moon raises tides in the oceans, and the sun helps too. On a giant planet extremely close to its star, the star's gravity can stretch the planet slightly, tugging at it again and again as it orbits. Over long periods, this tidal interaction can slow the planet's rotation until it becomes synchronized with its orbit. That is tidal locking. The planet turns once on its axis in exactly the same time it takes to orbit its star. One side always faces the star, the other side always faces away. This arrangement is hard for an Earth mind to settle into because our lives are built around rotation. Sunrise arrives, afternoon warms the day, evening comes, night falls, the ground cools, the next morning begins again. Our planet turns, and that turning gives us a rhythm so basic we barely notice it unless something interrupts our sleep. WASP-76b does not have that kind of daily cycle. There is no familiar sunrise sliding over the horizon, no sunset lowering the temperature, no morning birds, no evening shadows, no golden hour for alien photographers trying to get just the right shot of a metal cloud. Instead, the dayside is always day, and the nightside is always night. The star hangs fixed in the sky on one half of the planet, while the other half looks forever outward into space. That does not mean nothing moves. In fact, the atmosphere may move violently. When one side of a planet is heated constantly and the other side is cooler, pressure differences build. Hot gas expands. Cooler gas contracts. Winds form as the atmosphere tries to redistribute heat. On WASP-76b, those winds can carry material from the dayside toward the nightside, dragging heat, vapor, and chemical species along with them. The planet may be locked in place relative to its star, but its atmosphere is not frozen into stillness. It is more like a vast, restless engine. The star pours energy into one side. The air responds by moving. The movement creates a circulation pattern unlike anything in our own comfortable weather forecasts. The closeness to the star also means that the planet receives an overwhelming amount of radiation. Radiation is not just visible light. It includes ultraviolet and other forms of energy that can affect atmospheric chemistry. On ultra-hot Jupiters, the top of the atmosphere can become so strongly heated that molecules that would normally remain intact begin to split apart. Water vapor, for example, can be broken down on the hottest side of such planets. Other molecules can dissociate too, At lower temperatures, the atmosphere may be rich with familiar compounds. At higher temperatures, those compounds can break into atoms and ions. This makes the atmosphere less like a simple gas blanket and more like a chemical workshop running at dangerous speed. WASP-76b is especially interesting because the temperature is high enough for iron to enter the atmosphere as vapor on the dayside. On Earth, iron is something we mine, forge, build with and occasionally leave outside until it rusts. It feels solid and dependable. You do not expect it to be part of the sky, but in the furnace-like dayside of WASP-76b, the heat can push iron into a gaseous form. That is not because iron has become magical. It is because the planet's environment is extreme enough to make a familiar material behave in an unfamiliar way. The star does not care that iron feels solid in your hand. It only cares about energy, temperature, and pressure. Give iron enough heat under the right conditions, and even metal can become part of the air. The phrase, "too close to its star," can sound as if the planet made a poor decision, like it wandered into the wrong neighborhood and forgot to check the rental agreement. But planets do not choose their orbits. They arrive there through formation and migration, through the pull of gravity, through interactions with disks of gas and dust, through possible encounters with other planets, and through the long, complicated history of their star system. Hot Jupiters are one of the great reminders that planetary systems can rearrange themselves. Giant planets probably do not always stay where they formed. They can move inward or outward as they interact with the material around their young star. Some may be pushed into tight orbits, some may be scattered by gravitational encounters, some may settle into strange places that look surprising when compared with our solar system. Our own Jupiter stayed far from the Sun, and because of that, our solar system became the kind of place it is. The inner rocky planets remained small. Earth developed in a region where liquid water could persist. Jupiter's gravity shaped the asteroid belt and influenced the motion of comets. But in other systems, a Jupiter-sized planet can end up very close to its star. When that happens, it can shape the rest of the planetary system dramatically. It may clear out inner regions, disturb smaller planets, or migrate through areas where rocky worlds might otherwise form. WASP-76b is not only an extreme object by itself, it is evidence that planetary systems are not all arranged like ours. The universe has many ways to build a family of worlds, and some of those families are frankly less peaceful at the dinner table. A tight orbit also means speed. WASP-76b is moving quickly around its star, because the closer an orbit is, the faster a planet must travel to avoid falling inward. There is a simple balance at work. Gravity pulls the planet toward the star. The planet's sideways motion carries it around. In a wide orbit, that dance is slow. In a tight orbit, it is fast. A 1.8-day year is not just a measure of time. It is a sign of rapid motion under strong gravity. The planet is constantly falling around its star, missing it again and again, completing orbit after orbit with astonishing regularity. From far away, the system may look calm, just a star and a planet. Up close, it is a roaring gravitational dance. Because WASP-76b is so close, its star would appear enormous from the dayside sky. We have to be cautious with imagination here, because no one can stand on a surface and look up from WASP-76b. There may be no solid surface at all, and the atmosphere is too hot and dense for any ordinary observer. But as a way of picturing the geometry, the star would dominate the sky far more than our sun does from Earth. The dayside would not receive sunlight as a small bright disk surrounded by blue. It would be drenched in radiation from a nearby stellar face. The star would be a constant presence, always in the same place for that hemisphere, always pouring energy into the atmosphere. There would be no relief from rotation, no nightfall, no temporary turning away. The nightside, meanwhile, would be permanently shielded from direct starlight. That sounds at first like it might be cold, but cold is a relative term. The planet's nightside is still heated by winds, circulation, and the overall energy trapped in the atmosphere. It is cooler than the dayside, not cozy. It is the cooler room in a burning building, not a winter meadow. This distinction matters, because the night side does not need to be cold by Earth standards for iron to condense. It only needs to be cool enough compared with the dayside, under the pressure and chemical conditions of the atmosphere, for iron vapour to change form. That temperature difference across the planet is the engine behind the iron rain idea. Without the close orbit, there would be no dayside hot enough to vaporize iron. Without tidal locking, the contrast between constant day and constant night would be less extreme. Without winds, the vapour might not be carried from one region to the other. The story depends on all these pieces fitting together. There is something almost mechanical about it once you see the pattern. Close orbit brings intense heating. Intense heating expands the planet and changes its chemistry. Tidal forces lock the planet, so one side is always heated. The night side remains cooler. Winds connect the two halves. Materials vaporize, move, condense, and fall. The planet becomes a weather machine built by distance. Not a machine with gears, of course, but a natural system where gravity and radiation set the rhythm. The star does not simply illuminate WASP-76b, it organises the planet's whole atmosphere. And because the planet transits its star so often, that short year gives astronomers repeated chances to watch. Every 1.8 days, if the alignment is right from Earth, the planet passes in front of the star again. This is scientifically useful. A planet with a very long year might make astronomers wait months or years for another transit. WASP-76b returns quickly. It is almost impatient. Here I am again, it seems to say, crossing the light, offering another thin ring of atmosphere to the telescope. That repeating transit makes it a strong target for atmospheric study. Each pass gives scientists a little more information. Over many observations, the planet's extreme nature becomes clearer. The closeness also raises questions about how long such a world can remain in that orbit. Very close-in giant planets may experience atmospheric escape, where the upper atmosphere is heated enough that some gas can drift away into space. Tidal interactions can also affect the orbit over long timescales. Not every hot Jupiter is doomed quickly, and the details depend on the planet, the star, and their history. But the environment is not gentle. WASP-76b exists in a region where its star is not merely a distant source of daylight. It is a force that may slowly erode, inflate, reshape, and chemically transform the planet. The world is surviving, but it is surviving under constant pressure from light and gravity. It is worth taking a breath here, because the scale can become easy to say and hard to feel. A year shorter than a weekend, a giant planet nearly twice Jupiter's width, an orbit closer than Mercury's by a large margin, a star hotter than our Sun, a dayside hot enough for metal vapour. These facts line up neatly in a paragraph, but each one is enormous. We are talking about a planet hundreds of light years away, moving around its star with such speed that our ordinary calendar becomes almost meaningless. We are used to planets being steady things, moving slowly through space, marking seasons and ages. WASP-76b reminds us that some planets live fast. Their orbits are tight, their years are brief, their skies are violent, their atmospheres are stretched and cooked and driven around the globe. Still, the physics that explains it is the same physics that keeps Earth in orbit and gives us our own year. Gravity pulls, motion balances, radiation warms, atmospheres respond. The difference is intensity. Earth is placed at a distance where these processes produce oceans, clouds, and habitable weather. WASP-76b is placed where the same processes produce metal vapour, extreme winds, and permanent hemispheres of day and night. The universe is not using different rules. It is using the same rules with the dial turned very high. That is one of the reasons extreme planets are so useful. They show us what familiar physics can do when pushed far beyond familiar conditions. For a sleepy comparison, imagine leaving a pot of water near a warm window. It may slowly heat, perhaps evaporate a little. Move it onto a stove and the same water boils. Move it into a furnace and the situation becomes completely different. The substance has not changed its identity, but the environment has changed its behaviour. WASP-76b is like that, except the pot is a gas giant, the stove is an F-type star, and the kitchen is a gravitational system hundreds of light years away. The planet is not strange because physics breaks down there. It is strange because physics works perfectly well. This is also why calling it too close is partly a human judgment. From the planet's own point of view, if a gas giant may be allowed a point of view, there is no correct distance, no comfortable place it failed to choose. It is simply where it is. But from the perspective of the kind of worlds we know well, it is close enough to become extreme, too close for calm chemistry. Too close for an ordinary giant atmosphere, too close for gentle seasons, too close for the kind of weather that would make sense on Earth. Its short orbit is the root of its strangeness, the tight knot from which the rest of the story unravels. As we keep following this world around its star, the next question becomes unavoidable. What is actually happening on the side that always faces the light? Now that we have followed WASP-76b into its tight, rapid orbit, we can let our attention settle on the side of the planet that never escapes the star. Not a morning side, not an afternoon side, not a place where daylight comes and goes, but one permanent hemisphere held open to the heat. On Earth, day is temporary. It arrives, warms the ground, brightens the windows, moves across the sky, and then slowly hands the world back to evening. Even the hottest desert gets some kind of night. Even the most sun-baked stone eventually cools under darkness. But on WASP-76b, the dayside does not get that rest. It does not turn away. It does not wait for sunset. It stares constantly into its star, receiving light and heat again and again without the simple mercy of rotation. That one fact changes everything. We often think of heat as something that makes a place uncomfortable. A hot room, a summer pavement, a kettle boiling too long, a car left in the sun. But the dayside of WASP-76b is not hot in that everyday way. It is hot enough for chemistry to become strange, hot enough that materials we know as solid and stubborn can behave like part of the air, hot enough that some molecules struggle to remain molecules at all. This is a world where the star-facing atmosphere is pushed so far beyond ordinary planetary conditions that the sky itself becomes a kind of furnace. And because the planet is a gas giant, that furnace is not simply above the world. It is the world's outer skin, its visible weather, its moving, heated atmosphere. The dayside temperature of WASP-76b is often described as reaching thousands of degrees. Numbers like that are easy to say and hard to feel. A summer day on Earth might be 30 degrees Celsius and already make people sigh dramatically near open windows. A kitchen oven might reach a few hundred degrees. Lava from a volcano can glow orange at around 1,000 degrees or more. But WASP-76b's star-facing side rises into a temperature range where even metal can enter the atmosphere as vapour. Iron, the same element that helps make steel, the same element found in tools and buildings and the blood inside your body, can be heated until it no longer behaves like the heavy solid we know. It becomes part of the planet's air. That may sound almost impossible at first, because iron feels so deeply associated with solidity. If you hold an iron object or something made mostly of iron, it resists you. It has weight. It feels reliable. It is the kind of material humans use when they want something to last. Gates, beams, engines, cookware, railways, nails and old bridges all carry that feeling of iron as a firm thing, a serious thing, not something that drifts around like steam. On Earth, if iron is in the air, we usually mean tiny dust particles, pollution, or microscopic traces, not iron as a vapor filling the atmosphere of a planet. But the universe does not divide materials into categories based on how they feel in our hands. It asks about temperature, pressure, energy, and phase. Under one set of conditions, iron is solid. Under another, it melts. Under another still, it can vaporize. This is not really different from water, only more extreme. Water can be ice, liquid, or vapor depending on its environment. We know this so well that it barely feels like chemistry. Ice in a glass, rain on a road, steam from a kettle, mist over a lake. The same substance moves between states because heat is added or removed. Iron follows rules too. It just needs far more heat to make those changes. On WASP-76b, the dayside provides that heat. The star pours energy into the atmosphere so fiercely that iron atoms can be lifted into a gaseous state. Instead of forming part of a rock, a core, or a metal surface, iron can become a weather ingredient. It can be carried by winds. It can leave fingerprints in starlight. It can begin a journey that may end as rain on the night side. The source of this heat is not mysterious. WASP-76b orbits extremely close to its star, much closer than Mercury orbits the Sun, and its host star is hotter and brighter than our Sun. Distance matters in a very direct way. When a planet is close to its star, the light is more intense because the same stellar energy is spread over a smaller area. Move twice as close, and the energy does not merely double, it increases much more strongly. WASP-76b is close enough that its atmosphere is constantly soaked in stellar radiation. The star is not a gentle disk in the sky, it is a dominating force. On the dayside, it shapes temperature, chemistry, circulation, and perhaps even how high the upper atmosphere expands into space. Because the planet is likely tidally locked, the dayside keeps receiving this heat in the same region. There is no normal day-night cycle to move the heat evenly across the globe. Earth's rotation helps distribute solar energy. It gives each place a chance to warm and cool. Winds and oceans then carry heat around, smoothing some of the differences between regions. WASP-76b lacks that familiar rhythm. One hemisphere is always under direct stellar fire, while the other is always turned away. This does not mean the dayside is motionless. Far from it. The atmosphere is likely moving at tremendous speeds, driven by the enormous contrast between the hot side and the cooler side, but the heating pattern itself stays fixed. The star-facing hemisphere remains the receiving end of the planet's extreme energy. The result is a dayside that may be too hot for many molecules to survive intact. On cooler gas giants, molecules such as water vapor, carbon monoxide, or titanium oxide can help shape the atmosphere. On ultra-hot Jupiters, the dayside temperatures can become high enough to break some molecules apart into atoms. This is called thermal dissociation. A molecule is a group of atoms bonded together, but heat makes particles move faster and collide more energetically. If the energy becomes high enough, the bonds can break. So instead of a calm mixture of stable molecules, the upper atmosphere can become a restless soup of atoms, ions, and fragments. Later, when those materials move into cooler regions, some molecules may reform. The planet's chemistry is not fixed everywhere. It changes with longitude, altitude, temperature, and wind. That is a very different kind of atmosphere from Earth's. Our air is mostly nitrogen and oxygen, with water vapor, carbon dioxide, and other trace gases. It is thin, breathable, and pleasantly boring in a way we should be grateful for. The dayside atmosphere of WASP-76b is not breathable, not stable in the comforting sense, and not gentle. Hydrogen and helium likely make up much of the planet, as with gas giants generally, but the extreme heat allows heavier elements and metals to appear in the upper atmosphere in detectable forms. Iron, sodium, calcium, and other species can leave spectral signatures. These are not floating around as objects you could catch in a jar. They are atoms and ions interacting with light, absorbing very specific wavelengths, quietly announcing their presence across hundreds of light years. The way astronomers know this is by using light as a messenger. When WASP-76b passes in front of its star, some starlight filters through the outer edge of the planet's atmosphere. The atmosphere absorbs certain colours depending on what atoms and molecules are present. A spectrograph spreads that light into a detailed pattern, and scientists look for the missing pieces. Iron has its own pattern. It leaves a recognisable set of lines. That is how something as distant and unreachable as a planet's hot atmosphere can become a subject of measurement. We cannot scoop its air. We cannot send a weather balloon. We cannot hover beside it with a thermometer and a very brave clipboard. But light has passed through that atmosphere, and light remembers. On the dayside, scientists have also studied the planet's emitted light, not just the filtered light during transit. When the planet is about to pass behind the star, the hot dayside is facing us more directly. By examining the system before and after the planet disappears behind the star, astronomers can search for signals from the planet's own glowing atmosphere. This is difficult because the star is vastly brighter. It is like trying to notice the warmth of a candle beside a bonfire from miles away. But with high-resolution instruments and careful analysis, researchers can pull out faint signals. Recent work using espresso has reported neutral ion emission from the dayside, showing that iron is not merely part of a theoretical story, it is part of the observed atmosphere. That word, emission, gives us another glimpse into the dayside. In some hot atmospheres, certain layers can be hotter above cooler layers, creating what is called a thermal inversion. On Earth, temperature usually decreases with height in the lower atmosphere, though inversions can happen locally. In an ultra-hot Jupiter, strong absorption of stellar radiation by metals and other species can heat upper layers, producing conditions where atoms emit light in certain lines. This is one reason the dayside is so scientifically valuable. It is not just hot, it is structured. It has layers, circulation, and chemical behaviour that can be tested against models. The planet is extreme, but not unknowable. Its furnace atmosphere still follows rules. Imagine, in thought only, floating far above the dayside, protected by impossible technology that will not melt, crush, or politely evaporate. Below you, there is no blue sky, no white clouds, no sea glittering beneath sunlight. Instead, there is a vast, blazing atmosphere, bright with heat and stirred by violent motion. The star hangs fixed overhead, swollen and intense. The gases below are being heated so strongly that the ordinary idea of weather begins to stretch. In Earth weather, water vapour rises, cools, condenses and falls as rain. On WASP-76b's dayside, iron can enter the gas phase. This is where the metal rain cycle begins, not with falling droplets, but with vaporization. Before iron can rain, it must first become air. There is something oddly elegant about that. The nightside may get the dramatic image of iron falling from the sky, but the dayside is where the iron is lifted into the story. It is the source region, the furnace, the place where heat prepares the material for transport. Without the dayside, there would be no iron vapour for winds to carry. Without the close orbit, there would be no heat strong enough to put iron into that form. Without tidal locking, the planet might not maintain such a strong permanent contrast. The iron rain is not a separate oddity. It is part of a connected system. The dayside heats, the winds move, the nightside cools, the iron condenses. A whole cycle emerges from a planet being too close to its star. The phrase too close is useful, but it is also a little human. WASP-76b is not too close according to the universe. It is exactly where gravity and history have placed it. But from the perspective of a gas giant, this orbit is extreme. A planet like Jupiter formed in the cold outer solar system. Its atmosphere is deep, stormy, and complex, but it is not being blasted by sunlight at this intensity. If Jupiter were somehow moved inward to an orbit like WASP-76b's, it would not remain the Jupiter we know. Its clouds would change. Its upper atmosphere would heat and expand. Its chemistry would be rewritten. Its rotation might become locked. The familiar bands and storms could be overwhelmed by day-night circulation and stellar heating. WASP-76b shows us what a giant planet becomes when the star is not a distant lamp but a nearby furnace. Heat also affects the planet's size. WASP-76b is inflated, with a radius much larger than Jupiter's, despite having a mass in the same general range. This puffiness is common among many strongly irradiated hot Jupiters, though the exact mechanisms can be complicated. Stellar heating, atmospheric circulation, internal energy transport, and other processes may all contribute. From a simple point of view, the outer atmosphere is energized and expanded. The planet becomes physically larger than a cooler giant of similar mass would be. That larger radius makes the planet easier to detect in transit, because it blocks more of its star's light. It also gives its atmosphere a larger area through which starlight can filter. In a strange way, the very heat that makes WASP-76b so hostile also makes it more readable from Earth. The dayside is also important because it is probably not evenly hot from pole to pole and edge to edge. Atmospheric circulation can shift the hottest region away from the point directly beneath the star. On some hot Jupiters, winds move heat eastward, creating a hot spot offset from the substellar point, the place where the star would appear directly overhead. The details depend on wind patterns, rotation, magnetic effects, opacity, chemistry, and how quickly the atmosphere can radiate heat back into space. WASP-76b is not just a static ball with one hot half and one cool half. It is a moving atmosphere with currents, jets, and vertical motions. The dayside may have rising flows, shifting hot regions, and layers where iron and other atoms absorb and emit light. Even in permanent daylight, there is complexity. That complexity matters because when we talk about iron vapor, we're not imagining the whole atmosphere as a simple pot of boiling metal. The planet's atmosphere has pressure levels and temperature gradients. Different species exist at different heights. Some atoms may be ionized in upper layers, meaning they have lost electrons. Some may remain neutral. Some compounds may break apart on the dayside and reform elsewhere. Clouds may be absent on the hottest side because condensates cannot survive there, while the cooler regions may allow materials to form particles. Weather is not just what falls, it is the full pattern of movement, temperature, phase changes, and energy flow. On WASP-76b, the dayside is where that pattern begins under extreme illumination. There is a useful Earth comparison, even though Earth is far gentler. Think of the tropics, where strong sunlight heats the surface and drives convection. Warm air rises, water evaporates, clouds form, storms develop, and global circulation redistributes heat. The details are very different, but the underlying idea is familiar. Uneven heating drives atmospheric motion. On WASP-76b, the uneven heating is not between equator and pole in the ordinary way, or between land and ocean. It is between eternal day and eternal night. One hemisphere is continuously heated, creating a pressure and temperature imbalance so strong that winds may howl across the planet. These winds are the bridge between the furnace and the darkness. The dayside may also be stripped of many familiar cloud types. On cooler planets, clouds form when vapor condenses into droplets or particles. But if the dayside is hot enough to vaporize even refractory materials, substances that normally condense at high temperatures may remain gaseous. Iron, magnesium, silicon-bearing species and other materials may not form clouds where the heat is strongest. Instead, they can persist as vapour until they are transported to cooler regions. In this sense, the dayside is not where rain falls, it is where rain is prevented from forming. The atmosphere is too hot to let certain materials settle. It holds them aloft as gas, waiting for the winds to carry them toward a place where the temperature changes the rules. If you have ever watched steam rise from a kettle, you have seen a peaceful version of this idea. Near the heat, water becomes vapour and disappears into the air. Move that vapour toward a cool window, and it condenses into droplets. The material is the same, but the environment changes. WASP-76b takes that kitchen window lesson and rewrites it with iron, a giant planet, and a star. On the dayside, the iron is like steam. On the night side, it can become droplets or condensate. The scale is enormous, the temperatures are extreme, and the materials are unfamiliar for weather, but the basic physical idea is not beyond us. Heat turns a substance into vapour. Cooling brings it back out. The universe is very fond of simple rules wearing spectacular costumes. There is also a quieter reason the dayside matters. It tells us that exoplanets are not just defined by their average temperatures. If you average the temperature of WASP-76b, you get a useful number, but the average can hide the most important story. A tidally locked, ultra-hot Jupiter is not one uniform place. The dayside and nightside can be chemically different, thermally different, and dynamically connected. A planet's global average might tell you it is extremely hot, but the local conditions tell you whether iron vaporizes here, condenses there, or gets carried between regions. Weather lives in the differences. WASP-76b is a world of differences made permanent by its orbit. From Earth, the dayside is not always directly visible to us during transit. During the transit itself, we see mostly the planet's night side facing us as it crosses the star, with the atmosphere around the limb filtering light. Near secondary eclipse, when the planet passes behind the star, the dayside faces us more strongly. Astronomers use different orbital phases to study different parts of the planet. This is another reminder that exoplanet science is a game of geometry. What we know depends not only on what the planet is, but on how its orbit lines up with our view, where it is around its star, and what light reaches our instruments at each moment. WASP-76b is not sending us a simple portrait. It is offering glimpses from different angles, and scientists assemble them carefully. There is something almost restful in that patience, even when the planet itself is anything but restful. Humans sit on Earth beneath a calm night sky, using telescopes on mountain tops, gathering light that has crossed hundreds of years of space. That light carries the signs of heat, iron, motion, and atmosphere. Researchers compare spectra, remove the overwhelming signal of the star, correct for Earth's own atmosphere, account for orbital motion, and search for the tiny patterns left by atoms on a planet we will never visit. All to understand a dayside where metal becomes vapour. The scale of the work is quiet. The result is wild. It is tempting to picture the dayside as glowing red, like molten metal, but planets at these temperatures emit much of their energy in infrared light, with visible appearance depending on many factors. Artistic images often show hot Jupiters in fiery colours because that helps our eyes understand the heat. The real planet would be shaped by clouds or their absence, atmospheric absorption, thermal glow, and the intense light from its star. It may not look exactly like the illustrations, but the illustrations are useful emotional translations. They say, "This is a world under tremendous heat. This is not a blue sky. This is not a calm cloud deck. This is a planet where the atmosphere itself is being cooked." The dayside also challenges our instinct to separate planets and stars too sharply. WASP-76b is absolutely a planet, not a star. It does not fuse hydrogen in its core. It does not shine by the same process that powers its host. But its atmosphere is hot enough that some of the physics we might associate with stellar environments begins to appear in a planetary context. ionized metals, thermal inversions, high-energy radiation effects, strong emission features. It occupies a strange middle space in our imagination. Not a star, not a familiar planet, but an ultra-hot giant close enough to its star that its air becomes a laboratory for high-temperature physics. And still, beneath all the heat, the planet remains bound by the same quiet grammar of nature. The star gives energy, the gas absorbs it, atoms shift between states, winds respond to pressure differences, light carries information away, instruments gather that light, human minds turn it into a story. There is no need to exaggerate WASP-76b to make it astonishing. The real version is already enough. A giant planet with a year shorter than a weekend locked to its star, carrying iron in its atmosphere, heated so strongly that the familiar boundary between metal and weather begins to blur. Now the iron has left the furnace. It began on the dayside, where the star never sets, where heat pours into the atmosphere without pause, and where metal can be lifted into vapor, as if the sky itself has forgotten what solid things are supposed to do. But no atmosphere, not even one on a world as extreme as WASP-76b, is perfectly still. Gas moves, heat spreads, pressure differences tug at the air, winds reach across the planet, carrying material away from the permanent glare and toward the darker half of the world. And somewhere along that journey, as the star drops lower in the fixed geometry of the sky, and the atmosphere slips into the region that never faces direct daylight, iron begins to meet a different set of conditions. The metal that could survive as vapor in the fierce dayside heat is carried into cooler air, and there, far from anything we would call a gentle evening, it may begin to condense. This is the part of WASP-76b that gives the planet its unforgettable reputation. The nightside, where metal cools and falls as rain. Not rain as we know it, of course, not a soft shower tapping against leaves, not a grey afternoon drizzle that makes pavements shine, not the steady comforting sound you might hear from bed while the room grows quiet. This is a very different kind of rain, born from a very different sky. On Earth, water vapour rises, cools, gathers into clouds and returns as droplets. On WASP-76b, the dayside heat can turn iron into vapour, winds can carry that vapour around the planet, and the cooler night side may allow it to condense out of the atmosphere. The ingredient has changed, but the broad physical idea has a familiar shape. Heat lifts, cooling gathers, gravity pulls downward, weather happens. Still, it is worth saying gently that no one has watched iron raindrops falling there. No spacecraft has floated through the night side with a metal-proof umbrella, and no weather station has sent back a cheerful report saying, "Cloudy this evening with scattered iron showers after midnight." The planet is far too distant for that kind of direct observation. What astronomers have is more subtle and in its own way more beautiful. They have starlight, they have spectra, they have a signal of iron that appears in one part of the planet's atmosphere and not in another, suggesting that iron vapour is present where air moves from day to night, but depleted where air returns from night to day. The missing iron is the clue. Something seems to happen to it on the night side. The best explanation is that it cools, condenses and falls deeper into the atmosphere. There is something wonderfully detective-like about this. The rain is inferred from absence. Iron appears where the atmosphere has been heated and carried from the dayside. Then, after the air has crossed through the night, the same iron signal is no longer seen in the expected way. It is as if the planet has quietly taken the iron out of view, and when a vapour disappears after entering cooler conditions, condensation is a natural suspect. On Earth, you can see the same logic on a small, harmless scale when steam meets a cold window. The steam does not vanish into mystery, it becomes droplets. On WASP-76b, the window is not glass, the steam is not water, and the room is not a kitchen. But the change from vapour to condensed material follows the same deep habit of matter responding to temperature. The nightside of WASP-76b is often described as cooler, but cooler is a tricky word here. It can mislead us if we let it. Cooler does not mean cold. It does not mean icy plains, frozen valleys, or crisp air under stars. This is still an ultra-hot gas giant, orbiting extremely close to a bright star. The nightside is cooler only compared with the dayside, where temperatures are high enough to vaporize metals. Think of stepping away from a bonfire and into the edge of its light. You're cooler than you were beside the flames, but you're not in winter. Or imagine turning an oven down from impossibly high to merely dangerously hot. The word cooler is technically true, but it does not invite comfort. On WASP-76b, the nightside may be dark, but it is not gentle, and yet that difference is enough. Weather does not require Earth-like comfort. It requires gradients, changes, contrasts. On our planet, a modest temperature difference between warm ocean water and cooler air can help build clouds. A pressure difference can create wind. A cold front can lift warm air and bring rain. On WASP-76b, the contrast between the permanent day and permanent night is far more extreme. The dayside prepares iron as vapor. The nightside changes the rules and lets it condense. The whole planet becomes a stage for phase changes, with the star-facing hemisphere acting as the source of vapor, and the dark hemisphere acting as the place where that vapor is removed from the upper atmosphere. Try to picture the boundary between day and night on such a world. Astronomers call this boundary the terminator, a very dramatic word for the line between light and dark. On Earth, the terminator sweeps around the planet every day as we rotate, bringing sunrise in one direction and sunset in the other. On WASP-76b, because the planet is tidally locked, the terminator is not sweeping around in the same familiar way. It is more like a permanent twilight ring around the planet, dividing the hemisphere that always faces the star from the hemisphere that never does. Air crosses that boundary. Winds carry heat and chemical species across it. At one edge, material moves from day into night, and at the other, material moves from night back into day. Those two edges can have different chemistry, because the air has experienced different histories. That is a key idea. The atmosphere remembers where it has been. Gas arriving from the dayside may contain iron vapor, because it has just come from the furnace. Gas emerging from the nightside may have lost some of that iron because the iron condensed and settled. When astronomers study the planet during transit, they are effectively sampling the thin atmospheric rim around these regions. The evening side and morning side may not match. That mismatch is not a nuisance. It is the story. It tells scientists that WASP-76b is not a simple, evenly mixed ball of hot gas. It has weather patterns, circulation, and chemical changes from one longitude to another. It has a three-dimensional atmosphere doing three-dimensional things. The idea of metal rain sounds wild, but in a way it belongs to a larger family of exotic weather. Across the universe, weather does not have to be made of water. On Titan, Saturn's largest moon, methane and ethane play roles somewhat like water does on Earth, with clouds, lakes and rain under a cold orange haze. On some brown dwarfs, clouds may be made of minerals and silicates. On certain hot exoplanets, researchers consider the possibility of rock clouds, metal oxides, or other high-temperature condensates. Weather is not a specific substance. Weather is what an atmosphere does when energy moves through it. The substance depends on the world. Earth gives us water rain because Earth's temperature and pressure allow water to cycle beautifully between vapor, liquid, and ice. WASP-76b gives us the possibility of iron rain because its atmosphere lives in a temperature range where iron can vaporize on one side and condense on the other. There is a strange comfort in realizing that. The universe is not inventing chaos for its own sake. It is applying ordinary physical principles in extraordinary settings. If you know how steam fogs a mirror, you already have a tiny doorway into the logic of iron rain. Of course, the scale and the danger are entirely different. A bathroom mirror does not involve a gas giant larger than Jupiter racing around a star every couple of days. But the rule is familiar. Hot vapor moves into cooler conditions. Condensed material forms. Gravity does the rest. The universe often works this way, taking something you know from everyday life and then enlarging it until it becomes almost impossible to recognize. What would that metal rain be like? We have to be careful. The phrase can make us imagine heavy drops of molten iron falling, like orange sparks through a black sky, splashing into a deep metallic ocean. That image is dramatic, but the real process may be more complicated. The iron could condense into tiny droplets, particles, or clouds, depending on the pressure, temperature, and chemistry at different heights in the atmosphere. It might not fall neatly like Earth rain from a single cloud layer. It could settle downward through turbulent gas, evaporate again if it reaches hotter layers, or become part of deeper circulation. It may be more like a high-altitude loss of iron from the observable atmosphere than a storm you could stand beneath in the human sense. But even with those cautions, the phrase remains meaningful. Iron is likely leaving the vapor phase on the cooler side. It is condensing out. It is falling away from the upper air. That falling matters because it changes what astronomers see. If iron stayed as vapor all the way around the planet, its spectral fingerprint would appear more evenly. If it condenses on the night side, then the air returning from night to day may be iron poor in the upper layers. That is why the asymmetry is so important. It is not just that iron exists, it is that iron seems to be removed, and removal tells us about condensation. Condensation tells us about temperature. Temperature tells us about circulation. Circulation tells us about the whole climate of the planet. A missing line in a spectrum becomes a weather report from a place no human eye has ever seen. The night side itself must be a remarkable region, though not in a peaceful vacation way. There is no direct starlight, so the sky would not be lit from above by a fixed blazing sun. But the atmosphere may glow with heat, and winds may carry energy from the dayside. The darkness would not be like a cold Earth night under stars. It would be a deep planetary shadow filled with hot moving gas, chemical transitions, and falling condensates. The star would not rise, because the planet's rotation keeps that hemisphere turned away. If there is any glow, it would come from the atmosphere itself, from heat transported around the globe, from thermal radiation leaking into space, and from whatever high-temperature processes are taking place in the layers below. It is night, but not quiet. It is dark, but not calm. The permanent night side is also where the planet can try, imperfectly, to get rid of heat. On a tidally locked planet, the day side absorbs most of the star's radiation. The night side radiates some of that energy back into space after winds carry it over. The efficiency of this heat transport determines how extreme the day-night temperature contrast becomes. If winds move heat very efficiently, the night side warms more and the contrast weakens. If radiative cooling happens quickly and winds cannot carry enough energy, the contrast remains strong. For ultra-hot Jupiters, this balance is complicated. Their atmospheres can radiate energy quickly, but they also have fierce winds. WASP-76b sits in this dynamic struggle. Heat trying to spread, darkness trying to cool, chemistry responding along the way. The iron condensation is part of that struggle. When iron vapor crosses into cooler regions, it does not simply decide politely to rain. It responds to the local temperature and pressure. Every substance has conditions under which it prefers to be gas, liquid, or solid. In an atmosphere, condensation happens when the gas becomes saturated, meaning the air can no longer hold that material as vapor under those conditions. For water on Earth, saturation leads to cloud droplets and rain. For iron on WASP-76b, the saturation conditions are far hotter than anything in ordinary Earth weather, but the concept still applies. There is a point where the atmosphere can no longer keep iron in the gas phase. Then iron must become something else. It is possible to imagine an iron cloud layer, though again, The exact form depends on detailed models. Maybe tiny iron droplets or particles form in cooler nightside air. Maybe they grow large enough to settle downward. Maybe they fall into deeper, hotter layers and vaporize again, creating a kind of vertical cycle. Maybe some are carried farther by winds before disappearing from the observable region. Planetary atmospheres are not simple containers. They are moving, layered, turbulent systems. Earth's own rain cycle, which we learn as a tidy diagram in school, is much messier in real life. Clouds build and collapse. Droplets collide. Winds shear. Ice forms. Hailstones rise and fall inside thunderclouds. Now replace water with iron, move the whole process onto a giant exoplanet, and increase the temperature until ordinary intuition begins to sweat nervously. That is the kind of complexity scientists are trying to understand. The nightside may also be chemically rich, because many substances that are broken apart on the dayside can recombine when they reach cooler conditions. Molecules that cannot survive the full glare of the star may form again in the darkness. This means the atmosphere could be constantly changing its chemical identity as it moves around the planet. On the dayside, heat breaks things apart and vaporizes metals. On the night side, cooling allows condensation and perhaps molecular recombination. The winds carry not just heat, but a shifting chemical memory of where the air has been. In a sense, the atmosphere is always being cooked, carried, cooled, and rewritten. For us, the night side of WASP-76b is also a lesson in how misleading darkness can be. We often associate night with rest. The lights dim, the air cools, the world softens, creatures sleep, thoughts slow down, but night on another planet does not have to mean rest. On a tidally locked ultra-hot Jupiter, night is simply the hemisphere without direct starlight. It may still be hotter than lava. It may still be filled with roaring winds. It may still be a place where metal falls out of the sky. Darkness is not always peace. Sometimes darkness is just the other half of an extreme energy system, and yet there is a certain calm in the way the explanation unfolds. WASP-76b sounds impossible until you walk through it step by step. The planet is close to its star. It is tidally locked. The dayside is intensely hot. Iron vapor forms there. Winds carry the vapor toward the nightside. The nightside is cooler. Iron condenses. Condensed iron falls out of the upper atmosphere. Each step follows from the one before it. The final image is surreal, but the path to it is steady. This is one of the pleasures of science. It can take a phrase that seems like fantasy and build a staircase underneath it, one careful step at a time. It also reminds us why exoplanet atmospheres are so important. Finding planets is wonderful, but studying their atmospheres tells us what kind of worlds they really are. A planet's size and orbit give us the outline. Its atmosphere gives us the mood, the weather, the chemistry, the energy flow. Two planets with similar sizes can feel completely different if one has a calm atmosphere and the other has metal rain. WASP-76b is not interesting only because it is large or close to its star. It is interesting because its atmosphere reveals behaviour that stretches our imagination while still obeying physical law. It turns a distant dot into a place with a story. There is also a reminder here about Earth's own good fortune. Our rain cycle depends on water, and water rain is part of what makes our planet alive. It fills rivers, shapes landscapes, feeds plants, carries heat, and returns again and again in a cycle that has been running for billions of years. On WASP-76b, rain is not nurturing in that way. It is not watering forests or collecting in lakes under a friendly sky. It is a sign of extreme chemistry, a metal leaving the upper atmosphere because the temperature has dropped just enough. The word rain connects the two worlds, but the meaning changes. On Earth, rain can mean growth. On WASP-76b, rain means the dark side is cool enough for vaporized iron to fall. That difference makes Earth feel very particular. We do not just live on a planet with weather. We live on a planet whose weather suits us, at least often enough for life to have taken root. Our atmosphere is not too hot to hold metals as vapour. Our nights are not permanent hemispheres of darkness. Our winds do not carry iron from a star-facing furnace into a shadowed sky. We get clouds soft enough to watch, rain gentle enough to sleep beside, storms that, while powerful, belong to a planet with oceans and breathable air. Studying WASP-76b can make Earth seem smaller, but it can also make it seem kinder. The nightside, with its falling metal, is not just a curiosity. It is a natural laboratory for atmospheric circulation under extreme irradiation. Scientists can compare observations with models to ask how fast the winds move, how much heat reaches the nightside, where condensation occurs, and how chemical species are distributed around the planet. Different models may predict different patterns. Some may include strong eastward jets, others magnetic drag, others cloud formation or vertical mixing. Observations of iron and other species help test these ideas. The planet becomes a way to study the physics of atmospheres at temperatures we cannot reproduce on planetary scales here at home. And the more we learn, the less simple the phrase iron rain becomes. It remains a useful image, but behind it is a complicated circulation pattern. There are terminators, wind speeds, pressure levels, condensation curves, spectral lines, thermal structures, and perhaps variations over time. The planet may not behave exactly the same during every transit. Its atmosphere could be variable, with changing winds or temperature patterns. Recent observations continue to refine the picture, showing that WASP-76b is not just a solved riddle, but an active subject of research. The iron rain idea opened the door. Now scientists are exploring the room. For a moment, let your imagination drift to the nightside again, but carefully, not as a place to visit, only as a scene to understand. Above is darkness. Somewhere far around the curve of the planet, the star burns over the permanent day. Winds arrive from that blazing hemisphere carrying heat and vapour. The air cools as it moves deeper into shadow. Iron atoms that once floated freely begin to gather. Tiny droplets or particles form. They fall, pull downward into thicker layers. Perhaps they vanish into hotter depths. Perhaps they join clouds. Perhaps the cycle continues, lifted elsewhere, carried again, transformed again. The planet breathes in a way that is not biological, not alive, but still rhythmic. Heat, motion, cooling, condensation, fall. This is not a rhythm measured by Earth days because WASP-76b's day and year are locked together in that short orbit. It is a rhythm measured by circulation, by the time it takes winds to carry gas across hemispheres, by the cooling and heating of atmospheric layers, by the repeated transits that let us glimpse the process from far away. It is a different clock, written not in sunrise and sunset but in chemistry and wind. Every planet has its own way of keeping time. Earth turns, oceans respond, clouds gather, seasons shift. WASP-76b races around its star, fixed in day and night, while its atmosphere carries metal from light into darkness. The image of iron falling through an alien night may feel almost dreamlike, but it is grounded in a real question that scientists keep asking. How do atmospheres behave when they are pushed to extremes? This question matters beyond WASP-76b. There are many hot Jupiters and ultra-hot Jupiters, each with its own temperature, gravity, star, orbit, and atmospheric chemistry. By studying one in detail, astronomers learn tools and patterns that can be used on others. They can ask why some planets have strong day-night contrasts, while others distribute heat more evenly. They can ask which materials condense where. They can ask how clouds form when the clouds are made not of water, but of minerals or metals. WASP-76b is one world, but it belongs to a wider family of strange skies. Across the darkened half of WASP-76b, the story does not pause. it moves. The iron that cools and falls is not simply placed there by magic, and the nightside is not an isolated bowl of shadow collecting metal from nowhere. Something has to carry the vapor away from the furnace of the dayside. Something has to drag heat, atoms and chemical clues around a planet larger than Jupiter, through regions where the star hangs fixed in one sky and never appears in the other. That something is wind. Not the kind of wind that rattles a window or bends grass in a field, not the kind that makes you pull a coat tighter on a cold evening, but vast planetary winds moving through a deep heated atmosphere, crossing from permanent day toward permanent night, with enough force to turn chemistry into weather. On Earth, wind is familiar enough that we often treat it as background. It brushes past your face, carries the smell of rain, pushes clouds over a town, lifts leaves into small spirals on a pavement, and occasionally ruins a perfectly good umbrella with almost personal enthusiasm. But wind is really the atmosphere trying to balance itself. Air moves because one place is warmer or under different pressure than another. Warm air expands, cooler air sinks or contracts. Pressure differences form, and the atmosphere responds by flowing. It does not do this because it has a plan. It does it because gases follow gradients. They move from one condition toward another, turning uneven heating into motion. WASP-76b gives this simple idea a very extreme stage. One hemisphere is blasted by starlight all the time. The other hemisphere never receives direct light from the star. Between them lies a permanent contrast that Earth never experiences in quite the same way. On Earth, the day-night boundary moves because our planet rotates. Today's afternoon becomes tonight's dark, then tomorrow's morning. The atmosphere is always being stirred by a changing pattern of sunlight. On WASP-76b, the heating pattern is fixed. The dayside stays day. The nightside stays night. The hot region is always in the same broad place, and the cooler region is always opposite it. So the winds are not responding to a daily cycle like ours. They are responding to a permanent imbalance. That imbalance is enormous. The dayside can heat iron into vapor. The nightside can cool enough for that vapor to condense. Between those two conditions, the atmosphere becomes a moving bridge. Winds can carry iron vapor from the star-facing side into the dark hemisphere, where the temperature drops and the metal leaves the gas phase. In that sense, the winds are the delivery system for iron rain. The star makes the vapor. The air transports it. The nightside removes it. Without those winds, the iron rain story would not work in the same way. The dayside would be strange, and the nightside would be dark. But the cycle needs motion to connect them. It is easy to picture a single stream of air flowing neatly from day to night, like someone drawing one arrow on a diagram. And diagrams are helpful, especially when the alternative is trying to imagine a whole exoplanet's atmosphere at bedtime. But real atmospheres are more complicated. WASP-76b likely has broad circulation patterns, fast jets, vertical motion, turbulence, and different wind behaviour at different heights. The air near one pressure level may move differently from air higher up. Some regions may be dominated by day-to-night flow. Others may be shaped by rotation, waves, drag, or jet streams. The planet's atmosphere is not a smooth conveyor belt. It is a deep, restless system with layers, speeds, and directions that scientists are still trying to untangle. One reason these winds can become so fast is that the planet is very strongly heated from one side. When gas on the day side becomes hotter, it expands. That expansion helps create pressure differences between the heated side and the cooler side. The atmosphere then accelerates from one region toward another, trying to redistribute energy. But the planet is also rotating, and even though it is tidally locked, it still rotates once per orbit. That rotation can shape winds through the Coriolis effect, the same broad effect that helps organize large-scale weather systems on Earth. On a hot Jupiter, rotation and intense heating can produce powerful eastward jets, sometimes called superrotation, where winds near the equator move faster than the planet's rotation itself. It is a bit like the atmosphere deciding that the planet's pace is too relaxed and rushing ahead. For a world with a year shorter than a weekend, even its locked rotation is quick compared with many planets. It turns once every 1.8 Earth days, because that is how long it takes to orbit its star. That rotation, combined with huge day-night heating, helps create a complicated flow pattern. Some models of hot Jupiters predict that winds can push the hottest region away from the point directly under the star. Instead of the hottest spot sitting exactly at high noon, it may be shifted eastward by atmospheric motion. Heat does not simply stay where it arrives, the winds grab it and carry it along. WASP-76. B, in this way, is not a static world with one hot side and one cooler side. It is a planet where heat is constantly being dragged around the globe, even if the star itself never moves in the local sky. The winds also carry chemistry. That is the part that makes them especially important for the iron story. On the dayside, the air may contain iron atoms in vapor form because the temperature is high enough to keep them there. As those atoms are carried toward the night side, they travel with the wind, mixed into the flowing atmosphere. They do not know they are iron in the human sense. They do not know they once belonged in solid bridges, tools, rocks, or planetary cores. They are simply particles in hot gas, moving where the atmospheric flow takes them. Then the temperature changes. The gas enters cooler regions. The conditions that allowed iron to remain vapor no longer hold. The atoms can gather into condensates, droplets, or particles, falling out of the upper atmosphere. A wind-carried metal becomes nightside rain. Astronomers infer these winds through light, not by feeling them. No probe has flown into WASP-76b's atmosphere with a tiny windsock, which is probably for the best, because the windsock would have a very short and dramatic career. Instead, scientists look at spectral lines, especially how those lines are shifted and broadened. When atoms in a planet's atmosphere absorb light, they create features at very specific wavelengths. If the gas is moving toward us or away from us, those features shift slightly because of the Doppler effect. This is the same basic idea behind the change in pitch you hear when a siren passes by. Light has its own version of that shift. By studying tiny changes in spectral lines, astronomers can learn where the atmospheric gas is moving, and sometimes how fast. That is one of the most remarkable parts of this whole subject. The winds of WASP-76b are not heard, seen directly, or touched. They are read in the motion of the atoms through their effect on starlight. A line shifts slightly. A signal appears stronger on one limb of the planet than another. A pattern changes during transit. From those delicate clues, scientists begin to reconstruct the movement of an atmosphere hundreds of light years away. It is like listening to a song through a wall, hearing one note wobble and realizing the singer is walking across the room. Very difficult, slightly absurd, and somehow, with enough care, possible. High-resolution instruments are especially powerful for this. They can separate light into very fine detail, enough to distinguish the fingerprints of individual atoms and molecules and measure small velocity shifts. On WASP-76b, iron, sodium, and other species have been studied this way. Different atoms may trace different atmospheric layers or conditions. Sodium lines, for example, can be shaped by winds in parts of the atmosphere that are not exactly the same as those probed by iron. One study of the planet's atmosphere using harps and espresso explored strong day-to-night winds and even suggested vertical wind components in the upper atmosphere. That tells us the motion is not only horizontal, gas may also be moving upward and downward, connecting layers of different pressure and temperature. Vertical motion matters because an atmosphere has depth. It is not a painted surface. On Earth, rising air can create clouds, storms, and rain. Sinking air can clear skies. On WASP-76b, vertical winds may move hot material upward, bring material from deeper layers, or affect where atoms absorb light. If iron condenses and falls, vertical motion can influence whether it settles into deeper regions, evaporates again, or gets mixed back upward. The phrase, "winds carry metal around the planet," sounds horizontal, as if iron vapor is simply swept from left to right around a globe. But the real picture may include updrafts, downflows, slanted jets, shearing layers, and different speeds at different heights. The metal is not just travelling around, it may also be travelling through. The terminator regions, those permanent borders between day and night, are especially important. During a transit, when WASP-76b crosses in front of its star, starlight passes through the planet's atmospheric rim. That rim includes the morning side and evening side depending on where the air is moving from and to. If the evening side is receiving air from the day side, it may be hotter and richer in iron vapour. If the morning side contains air that has passed through the night side, it may have lost some iron to condensation. Scientists have found evidence that the two limbs do not look identical in iron absorption. This asymmetry is one of the clues that the winds and temperature differences are organising the atmosphere in a strongly three-dimensional way. That may sound technical, but the heart of it is simple. Air has a history. Air that has just come from the day side is not the same as air that has crossed the night side. The planet's atmosphere is like a traveller carrying souvenirs from where it has been. From the day side, it carries heat and vaporized metal. From the night side, it carries the evidence of cooling and condensation. When starlight passes through that air, it reveals the journey. The spectrum is not just a list of ingredients. It is a travel diary written in absorption lines. Earth's winds also carry things around the planet. They carry dust from deserts across oceans. They carry volcanic ash through the sky. They carry moisture from warm seas into storms that later drop rain over land. They carry pollen, smoke, salt, and sometimes the smell of someone's barbecue from several gardens away, which can be either pleasant or deeply unfair depending on your dinner plans. On WASP-76b, the transported material can be metal vapour. The comparison is not perfect, but it helps. Wind is a courier. It picks up what the environment allows and moves it somewhere else. The cargo depends on the world. The speed of these winds is difficult to imagine. Some analyses suggest flows of several kilometres per second in parts of WASP-76b's atmosphere. A kilometre per second is already much faster than anything we call wind in ordinary weather. Earth's strongest hurricanes have winds measured in tens or sometimes over 100 metres per second, which is terrifying enough. Several kilometres per second belongs to a different category of atmospheric violence. Yet even that violence has structure. It is not random shouting by the sky. It follows from pressure gradients, radiation, rotation and gravity. The atmosphere is behaving according to physics, even if the result would make every Earth weather app give up and quietly uninstall itself. The winds also influence how much heat reaches the night side. If they are efficient, they can warm the night hemisphere and reduce the temperature difference. If radiative cooling is too fast, the air may lose heat before it travels far, leaving the day side extremely hot and the night side much cooler by comparison. Ultra-hot Jupiters often exist in this tension. Their atmospheres absorb enormous heat, but they may also radiate energy away quickly. The winds are trying to share the warmth. Space is trying to take it away. The final climate depends on which processes dominate at each altitude and location. WASP-76b's iron rain tells us that the night side is cool enough, at least in some regions and layers, for iron to condense out. That means the winds carry iron there, but they do not erase the contrast completely. This makes the planet a useful test for atmospheric models. Scientists build computer simulations called General Circulation Models, or GCMs, to describe how gases move on planets. These models include heating, cooling, rotation, pressure, and sometimes chemistry or cloud formation. Earth weather forecasting uses related principles, though Earth is different in many ways because it has oceans, land, water clouds, and a much milder temperature range. For hot Jupiters, the models have to handle huge irradiation, possible tidal locking, strong winds, and unfamiliar chemistry. WASP-76b gives researchers a real case to compare against. If the models can reproduce the observed ion asymmetry, wind signatures, and temperature differences, scientists gain confidence that they understand some of the physics. If not, the planet is politely pointing out that something is missing. And planets are very good at that. They expose the gaps in our understanding without saying a word. A spectral line is stronger than expected. A wind speed looks too high. A signal appears on one limb but not the other. A model predicts iron where the observation suggests it has vanished. Each mismatch is not a failure in the discouraging sense. It is an invitation. Nature is saying, look more carefully here. WASP-76b, with its metal-carrying winds, is especially good at offering invitations. Its atmosphere is large, hot and observable enough to reveal details, but complicated enough to keep scientists busy. There is another layer to consider: magnetic effects. At very high temperatures, some atoms can lose electrons and become ionized. Ionized gases can interact with magnetic fields. This may create a kind of drag on winds, slowing or reshaping atmospheric flow. Ultra-hot Jupiters may be hot enough for magnetic processes to matter in ways they do not for cooler planets. The details are complex and not every effect is fully settled, but the possibility adds to the picture. WASP-76b's winds are not just ordinary gases sliding around. They may involve partially ionized material, strong radiation, and interactions between chemistry, temperature, and magnetism. The sky becomes a place where weather begins to overlap with plasma physics. For all that complexity, the image remains beautifully understandable. A giant planet sits too close to its star. The dayside heats until iron becomes vapor. The atmosphere cannot stay still. Winds rush around the planet. They carry the iron into shadow. Cooling changes vapor into condensate. Metal falls away. Then the air continues moving, perhaps iron poor now, perhaps ready to be reheated as it returns toward the light. The cycle may repeat, not like a neat circle drawn in a schoolbook, but like a turbulent loop in a world-sized furnace. It is weather, but weather rewritten by a star. The scale of the motion is worth resting with for a moment. We are not talking about a breeze crossing a field. We are talking about flows that may span an entire gas giant, moving through an atmosphere swollen by heat, around a planet whose circumference is far larger than Earth's. The winds connect hemispheres that are locked into permanent rolls. They move between a dayside where metal can float as vapor and a nightside where it can fall. They cross the terminator, that fixed ring of transition, and carry with them the chemical consequences of each region. Somewhere in that motion, iron changes state. Somewhere in that motion, a spectral signal disappears. Somewhere in that motion, a distant planet becomes understandable. It is also useful to remember that these winds do not carry iron in the way a human hand carries a bucket. The iron is part of the gas, mixed into the atmosphere at the atomic level. It travels because the gas travels. When conditions change, the iron's relationship to the gas changes. It condenses, it forms particles or droplets, it may settle, it may be mixed. It may evaporate again in deeper or hotter regions. This is atmospheric chemistry coupled to atmospheric dynamics. The movement and the chemistry cannot be fully separated, because each shapes the other. The wind decides where the iron goes, the temperature decides what form it takes, the condensation changes what remains in the observable air. There is a mild irony in the fact that WASP-76b's winds, so violent in reality, are known to us through such quiet methods. A telescope mirror collects light. A spectrograph separates it. A computer removes noise. A researcher examines patterns. The result is a glimpse of a roaring atmosphere delivered through numbers on a screen. The universe often works like that for us. The loudest places arrive silently. Supernova remnants, black holes, stellar winds, and metal rain all reach us through photons, tiny messengers that travel for years and years before landing in an instrument. We sit in relative calm and read the violence from afar. This distance is part of the wonder. If we were too close to WASP-76b, it would be lethal. From here, it can be understood. It becomes a lesson rather than a danger. We can think about its winds while lying under a blanket on a quiet night. We can let the idea of iron vapour travelling across a planet become not frightening, but fascinating. Science gives us that gift. It lets us approach the extreme without being consumed by it. It turns a hostile world into a story about heat, motion, chemistry, and light. The winds of WASP-76b also remind us that planets are not merely objects, they are systems. A planet is not just its mass, radius, and orbit. It is the interaction of its star, atmosphere, gravity, rotation, chemistry, and history. WASP-76b's metal rain cannot be understood by looking at one fact alone. The short orbit matters, the stellar heat matters, tidal locking matters, the day-night contrast matters, the winds matter, the condensation matters, the observations matter. Each piece is connected to the others, and the planet becomes real to us through the network. As the air keeps racing around WASP-76b, it carries more than iron. It carries the central question of this world. What happens when a giant planet is forced to live with one face forever turned toward its star? On WASP-76b, noon is not an hour on a clock. It is a place. It is a whole hemisphere of the planet fixed beneath the glare of its star, held there by gravity and time until daylight no longer behaves like something that arrives and leaves. Here on Earth, noon passes over us and moves on. It brightens the street, warms the roof, climbs through a window, and then slowly slips away toward afternoon. We measure it, miss it, wait for it, schedule lunch around it, and occasionally blame it for making a room too warm. But on the day side of WASP-76b, noon does not pass. It remains. The star stays in the same region of the sky, pouring heat into the atmosphere without a sunrise to begin it or a sunset to end it. That is what tidal locking does to a world. It ties the planet's rotation to its orbit so closely that the same face always points toward the star. The moon is tidally locked to Earth, which is why we always see the same familiar side from our planet. The far side exists, of course, but it never turns toward us in the ordinary course of the moon's motion. WASP-76b has a similar kind of locked relationship, but with far more extreme consequences. Instead of one lunar face always watching Earth, one hemisphere of a giant exoplanet always watches a star. And because that planet orbits so close to its star, the result is not just a near side and a far side. It is eternal day and eternal night. The phrase eternal day sounds peaceful at first, perhaps like a long summer evening that forgot to end. But on WASP-76b, permanent daylight is not a soft golden afternoon. It is relentless heating. It is an atmosphere constantly bombarded by radiation. It is a star-facing region where temperatures climb high enough to turn iron into vapour. The dayside is not a place with weather in the earthly sense of blue skies and drifting clouds. It is more like a giant atmospheric furnace, with gases expanded by heat and chemistry pushed into states that would seem impossible at ordinary temperatures. If daylight on Earth helps flowers open and mornings begin, daylight there breaks molecules apart and lifts metal into the air. The night side, meanwhile, is just as strange in the opposite direction. It is not night because the planet turns and gives that region a few hours of darkness. It is night because it never faces the star at all. There is no dawn waiting under the horizon, no pale line of morning, no sun rising after a long cold stretch. The same half of the planet remains turned away into space, receiving only the heat that winds and circulation can carry from the day side, And even though it is cooler than the star-facing side, it is still extremely hot by any human standard. It is a darkness made for metal condensation, not for frost on grass or quiet breathing under an open sky. This locked arrangement is one of the main reasons WASP-76b can have such dramatic chemistry. A rotating planet like Earth spreads sunlight around itself. Every place, except near the poles in certain seasons, moves through light and dark. Even hot places get night. Even cold places receive daylight eventually. This constant rotation helps prevent one side from being permanently cooked, while the other remains permanently shielded. WASP-76b does not share that relief. Its heating pattern is frozen into place. One side is always being energized, the other is always trying to cool. Between them, the atmosphere has to move. The border between the two halves is called the terminator. On Earth, the terminator is the moving line between day and night, sliding around the globe as the planet spins. If you could watch Earth from space, you would see that line sweep across continents and oceans, bringing morning to one side and evening to another. Cities would light up behind it. Clouds would glow near it. It would move steadily because Earth turns once every day. On WASP-76b, the terminator is more like a permanent ring around the planet, marking the transition between star-facing day and starless night. It is not a sunrise line travelling across the world. It is a fixed boundary in the planet's relationship with its star. That boundary matters because astronomers often study WASP-76b during transit, when the planet passes in front of its star from our point of view. During that crossing, starlight filters through the thin outer rim of the planet's atmosphere. That rim includes the terminator regions, where the atmosphere is neither fully dayside nor fully nightside in a simple way, but part of the transition. One edge is like evening, where air has been carried from the hot dayside toward darkness. The other is like morning, where air has passed through the night side and is returning toward the light. These are not mornings and evenings with sunrises or sunsets as we know them. They are directions of travel through a locked atmosphere. Still, the comparison helps. Evening air has recently come from the furnace. Morning air has crossed the dark. This is why WASP-76b's two limbs can reveal different chemical signals. Air that has just left the dayside may still contain iron vapor. Air that has crossed the night side may have lost some of that iron because it condensed and fell out of the upper atmosphere. The planet's locked day-night structure gives the atmosphere a memory. Where the air has been changes what the air contains. The evening terminator and morning terminator are not identical doors into the same room. They are different parts of a moving system, and light passing through them carries different messages. It is a helpful reminder that tidally locked planets are not simply split into two static halves. The phrase eternal day and eternal night might make us imagine one bright side sitting still, and one dark side sitting still, like two painted faces on a ball. But the atmosphere is alive with motion, not alive biologically of course, but active, flowing, and constantly responding. Heat creates pressure differences, winds race between regions, jet streams may wrap around the planet, material rises, cools, sinks, condenses, and moves again. The surface pattern of light is fixed, but the atmosphere is restless. Earth's atmosphere is shaped by motion too, but our motion has different causes and rhythms. Our planet rotates quickly enough to create daily cycles. The sun heats the ground and oceans unevenly. Land warms faster than water. The equator receives more energy than the poles. Seasons shift the pattern through the year. The Coriolis effect organizes moving air into spirals and bands. Weather grows from all these differences. WASP-76b has no oceans or continents in the usual sense, and its day-night contrast is far more severe. Its weather is shaped by the permanent face-off between the hot hemisphere and the cooler, dark hemisphere. If Earth's atmosphere is like a constantly changing conversation, WASP-76b's atmosphere is more like a long argument between two sides that can never trade places. The dayside is always receiving the star's energy. The nightside is always radiating heat away into space. Between them, winds act as negotiators, carrying energy from one side to the other. They do not erase the difference completely, but they prevent the two hemispheres from being entirely isolated. This is why the nightside is not cold in any ordinary sense. Heat from the dayside is transported around the planet. The atmosphere itself becomes the bridge. But because the nightside still remains cooler than the dayside, it can allow materials such as iron to condense. The planet's locked state creates both connection and separation. It allows winds to move material around while preserving enough contrast for metal rain to happen. There is an interesting contrast with the moon. The moon is tidally locked to Earth, but it still has day and night because it orbits Earth while both travel around the sun. Every part of the moon receives sunlight during its long lunar day, and then darkness during its long lunar night. Its locking means the same face points toward Earth, not that the same face always points toward the sun. WASP-76b is different because it is locked to its star. The same side faces the source of heat and light. That is why the effect is so extreme. The effect. The star is not a distant observer. It is the furnace at the centre of the planet's orbit. The locking likely happened because the planet is so close to its star. Tidal forces are stronger at short distances. Gravity pulls more strongly on the near side of a planet than the far side, creating tidal bulges and internal friction. Over time, that friction can slow or adjust a planet's rotation until it matches the orbital period. For WASP-76b, with an orbit of about 1.8 Earth days, the locked rotation means the planet turns once in that same time. To the star, the planet always presents the same face. To the planet, the star stays fixed. It is a gravitational arrangement that turns time into geography. That idea is worth resting on for a moment. Time becomes geography. On Earth, day and night are times. On WASP-76b, they are locations. You would not ask what time sunrise is on the dayside because sunrise is not coming. You would not wait for midnight on the night side because midnight is already the permanent condition. Instead of a clock cycling through light and dark, the planet has a map divided into light and dark. If there were a weather forecast there, which again would be a brave and short-lived service, it would not say cooler after sunset. It might say cooler if winds carry you far enough toward the night hemisphere, which is less catchy but much more accurate. This changes how we think about climate. On Earth, climate is tied to latitude, seasons, oceans, mountains, and long-term circulation. On a tidally locked hot Jupiter, climate is tied strongly to longitude, meaning where you are relative to the substellar point, the spot where the star would be directly overhead. At the substellar point, the heating is strongest. Moving away from that point toward the terminator, the star would appear lower in the fixed sky, and the heating would change. Crossing into the night side, direct stellar radiation disappears. Instead of north and south being the main temperature story, day-facing and night-facing regions become essential. The planet's climate is organised around its starward face. The substellar point itself is almost like the centre of the planet's permanent day. It is the place where the star hangs overhead, never drifting, never lowering. Around it, the atmosphere receives intense radiation. But even there, the hottest atmospheric region may not sit exactly under the star, because winds can carry heat sideways. On many hot Jupiters, atmospheric circulation can shift the hotspot eastward. The planet's locked geometry sets the basic pattern, but winds modify it. That makes the planet more complicated than a simple bright half and dark half. It is locked, but it is not simple. It is permanent, but not still. The night side also has structure. It may not be one uniform dark blanket. Heat carried by winds may warm some regions more than others. Air flowing from day into night may cool gradually, causing different substances to condense at different places and altitudes. If iron condenses in one part of the night side, other materials may condense elsewhere depending on their own chemistry. Some molecules broken apart on the dayside may recombine in the cooler darkness. The nightside is not merely the absence of light, it is an active chemical region where the atmosphere changes form after leaving the heat. This is one of the reasons WASP-76b is so valuable to scientists. It lets them study how atmospheres behave when exposed to fixed, extreme irradiation. The planet is not habitable, not gentle, and not remotely Earth-like, but it offers a clear test of atmospheric physics. Models can predict how heat should move from day to night, how winds should flow around a tidally locked gas giant, and where condensation should occur. Observations can then test those predictions. If the observed ion signal is stronger on one limb than another, that tells scientists something about the planet's circulation and temperature patterns. If other metals or atoms show different patterns, that adds more detail. The locked day-night system becomes a laboratory. There is also a broader reason this matters. Tidally locked planets are common in exoplanet science, especially for worlds orbiting close to their stars. Many small planets around red dwarf stars may also be tidally locked because they orbit close enough for tidal forces to synchronize their rotation. Those worlds are very different from WASP-76b, but the basic question of permanent day and night appears again. Could an atmosphere move heat from one side to the other? Could the night side become too cold? Could the day side lose water? Could life exist near the terminator of a smaller, cooler, tidally locked planet? WASP-76b is far too hot for life as we know it, but studying its extreme circulation helps scientists understand the wider family of locked worlds. For a smaller rocky planet, tidal locking might create a permanent dayside desert and a permanent nightside ice sheet, with a more moderate twilight region between them. For WASP-76b, the same concept is pushed into the realm of vaporized metals and giant winds. It is the extreme version of a question that appears across planetary science. What happens when one side of a world always faces its star? The answer depends on atmosphere, distance, star type, rotation, pressure, and chemistry. WASP-76b gives us one answer at the hot, giant, dramatic end of the scale. The psychological effect of imagining such a place is strange. We are creatures of cycles. Our bodies expect morning and night. Our sleep is tied to darkness. Our moods often follow light. Plants open and close with the sun. Animals migrate, hunt, rest, and wake, according to rhythms that depend on Earth's rotation and orbit. A world without moving sunrise feels almost wrong to us. Eternal day seems exhausting. Eternal night seems lonely. But those feelings come from being Earth-made creatures. WASP-76. B does not miss sunrise. It has no forest waiting for dawn, no animals looking for shade, no oceans reflecting sunset. It simply exists in the arrangement gravity has given it. The strangeness is ours. Still, using human comparisons helps us understand the physics. Imagine standing in a room where one wall is an enormous heater that never turns off, while the opposite wall opens into cold darkness. Air would move, heat would flow, the room would not settle into a calm, even temperature easily. Now imagine that room is larger than Jupiter, made of deep gas, spinning in a locked orbit, and filled with materials that can change phase under extreme heat. That is not exactly WASP-76b, but it nudges the mind in the right direction. Permanent heating on one side creates permanent circulation. Permanent darkness on the other creates permanent cooling. Between them, chemistry becomes weather. The locked state also affects how the planet appears from far away. As WASP-76b orbits its star, different portions of its dayside and nightside face Earth depending on where it is in its orbit. When it transits, we mostly see the planet's night side against the star, with its atmospheric rim filtering starlight. When it moves behind the star in secondary eclipse, The dayside is the part that had been facing us just before it disappears. By comparing light from different orbital phases, astronomers can learn about the planet's brightness distribution and temperature patterns. The locked geometry gives the orbit a repeating pattern of visible hemispheres. Each phase offers a different glimpse. In that sense, even though WASP-76b has no ordinary sunrise, we have our own version of watching its phases from Earth. Not visually in a backyard telescope, of course, but through careful measurements of light. The planet reveals different faces as it circles its star. Its dayside glows more strongly in thermal emission. Its nightside contributes less. Its atmosphere filters starlight at transit. The data is faint, but the pattern is there. The locked world turns around its star, and we slowly learn what each side is doing. It is important not to imagine a hard line where day instantly becomes night, like stepping from one room into another. The terminator is a region, and atmospheric conditions change gradually across it. Winds blur the boundary, heat is carried, chemistry lags behind temperature. A parcel of gas may still contain materials from the dayside as it enters darkness. Another may be chemically changed before it returns to light. The planet's permanent divide is real, but the atmosphere makes it dynamic. It smears, shifts, and complicates the simple picture. That complication is not a problem. It is the planet being real. The eternal day and night also raise questions about clouds. On the hottest dayside, many condensates may not survive. The atmosphere may be relatively clear of certain clouds because materials remain vaporized. On the cooler night side, clouds made of exotic materials may form. Those clouds could affect how heat is trapped or radiated, how light is absorbed, and where different species appear in spectra. If iron condenses, it might be part of cloud formation or rainout. Other minerals could also condense under the right conditions. A tidally locked planet may have clouds that prefer the night side, not because the night side is Earth cold, but because it is cool enough for high-temperature materials to gather. The sky's appearance could vary greatly from one hemisphere to the other. This is another way in which WASP-76b differs from Earth. Our clouds often form because water vapor rises and cools. They can appear in day or night, over land or sea, shaped by local weather. On WASP-76b, clouds may be controlled by the permanent temperature map. Some materials may be impossible to condense on the dayside and possible on the night side. The planet's locked state could create chemical zones, where substances appear, disappear, or change form depending on their journey around the globe. A cloud on WASP-76b may tell you not just about moisture, but about whether the air has crossed into darkness. For all its extremity, the locked day-night pattern gives the planet a kind of understandable order. It is not random. It has a source of heat, a region of cooling, and winds connecting them. The star-facing side creates vapor. The night side removes some of it. The terminator regions reveal the difference. Scientists can build models around that structure. Without tidal locking, the planet would still be hot because it is close to its star, but the weather might be distributed differently. The permanent hemispheres sharpen the contrast. They make the iron rain cycle more plausible and more visible in the data. There is a gentle irony in calling any part of WASP-76b night. On Earth, night is a time when stars become visible, when cities glow, when the air cools and the mind begins to loosen its grip on the day. On WASP-76b, night is not restful. It is the shadowed half of a giant planet still heated to extreme temperatures, swept by violent winds, and possibly filled with falling metal. But the word night still helps us. It tells us that the star is absent from that sky. It tells us that direct light does not reach that hemisphere. It gives us a handle, even if the thing we are holding is much stranger than the handle suggests. The same is true of the word day. Day on Earth implies wakefulness, warmth, and light. Day on WASP-76b implies relentless irradiation, chemical dissociation, and metal vapor. We use familiar words because they are the bridge from our world to another. Then science carefully explains where the bridge ends. Day and night exist there, but not as times. Rain exists there, but not as water. Wind exists there, but not as a breeze. A planet exists there, but not as a place with ground beneath your feet. Each familiar word opens the door, and each explanation expands the room beyond what we expected. As we keep drifting around this locked world in thought, the permanent divide becomes the key to everything. It explains why the dayside can be hot enough to vaporize iron. It explains why the nightside can be cooler enough for iron to condense. It explains why winds must carry material between regions. It explains why the atmosphere looks different at different limbs during transit. The planet's geometry is not just a background detail. It is the engine of its weather. Weather does not have to be friendly to be weather. That might be the first quiet lesson WASP-76B offers us, from its bright star-facing furnace to its dark metal-raining night. Here on Earth, when we hear the word weather, we usually imagine things we know: clouds gathering over a town, rain sliding down a window, wind moving through trees, snow softening the sound of a street, thunder rolling somewhere beyond the hills. Even when Earth's weather becomes dangerous, it is still made from familiar ingredients: water, air, heat, dust, pressure, and the turning of our planet beneath the sun. We live so completely inside Earth's weather that it can feel like the default setting for the universe. But WASP-76B reminds us that Earth weather is only one version of a much larger idea. On that faraway giant planet, weather is not built around oceans, rivers, and water vapor. It is built around extreme heat, rapid winds, permanent day and night, and materials that would never behave this way in our everyday lives. Iron, which feels solid and heavy on Earth, can become part of the air on the dayside. Then, when the winds carry it toward cooler darkness, it can condense and fall out of the atmosphere. That is the same basic logic that gives Earth rain, but with a different ingredient and a far more extreme environment. It is not gentle, but it is still weather. It is an atmosphere responding to energy, moving material from one place to another, changing the form of that material as temperature and pressure change. This is what makes the iron rain so useful to scientists. It is not only a strange fact that sounds good in a title, it is a clue. It tells us that the planet has a strong day-night temperature difference. It tells us that winds are carrying material from the hot side to the cooler side. It tells us that iron can exist as vapor in one region and condense in another. It tells us that the atmosphere is not the same everywhere. In other words, the iron rain is not just decoration in the story of WASP-76B, it is evidence of a whole climate system. On Earth, we often understand weather by watching it directly. We see clouds build. We feel humidity. We hear rain. We watch the forecast, sometimes with trust, sometimes with the expression of someone who brought the wrong coat. But on exoplanets, astronomers cannot watch weather in that direct way. They cannot see an iron cloud forming over WASP-76b in a telescope image. They cannot track a storm system across its nightside with visible photographs. The planet is too far away and too close to its bright star from our point of view. Instead, they read the weather through light. A chemical signal appears in one part of the atmosphere and not another. A spectral line shifts. A planet blocks a little starlight. The details are small, but the meaning can be enormous. The iron signal on WASP-76b matters because it appears uneven. If the atmosphere were simple and well mixed, iron vapor might appear in a more uniform way around the planet's limb. But the observations suggest a difference between the side where air is moving from day into night and the side where air has passed through night and is returning toward day. That difference is what turns chemistry into meteorology. It says the atmosphere has direction. It says that air carries a history of where it has been. It says the night side changes the air before that air returns to the light. You can think of it in a very ordinary way, using a cup of tea on a cool evening. Steam rises from the hot surface, but when it touches a cold window, it condenses into droplets. If you knew nothing about the room, but you saw steam in one place and droplets on the glass in another, you could infer something about heat, cooling, and movement. WASP-76b is much more extreme, of course. The T is an ultra-hot gas giant. The window is a permanent nightside region. The steam is iron vapour. The room is hundreds of light years away, but the logic has a similar shape. A material changes form when its environment changes. That is one of the biggest lessons alien weather teaches us. Weather is not the same as water. Water is simply the substance that dominates weather on Earth, because Earth has the right temperature and pressure for water to move easily between solid, liquid, and vapour. Our planet's weather feels water-based because our planet lives in a water-friendly range. Change the temperature enough, and another substance can take the leading role. On Titan, Saturn's large moon, methane and ethane can condense, rain, and collect in lakes and seas under a cold orange atmosphere. On some very hot worlds, silicates, metals, or mineral compounds may become part of clouds. On WASP-76b, iron becomes part of the weather story because the temperatures are high enough to put it into the air, and different enough between hemispheres to take it back out again. This expands the meaning of weather in a very practical way. Weather is the behaviour of an atmosphere under changing conditions. The atmosphere may be nitrogen and oxygen, like ours. It may be mostly hydrogen and helium, like a gas giant's. It may include methane haze, metal vapour, mineral clouds, or molecules broken apart by radiation. The details vary, but the underlying question is the same. How does energy move through the system? Where does heat enter? Where does heat escape? What materials are present? Which of those materials can condense? How fast do winds carry them? How does gravity pull them downward? How does light reveal them from far away? WASP-76b answers these questions in a dramatic way because it is tidally locked. One side always faces the star and the other side always faces away. This gives the atmosphere a permanent heating pattern. The dayside is the source of intense energy. The night side is the cooler region where some materials can condense. The terminator, the border between day and night, becomes a place where changing chemistry can be observed. This is very different from Earth, where every location moves through day and night because the planet rotates. On WASP-76b, day and night are not times on a clock. They are places on a map. That turns the planet into a natural experiment. What happens when one side of a giant atmosphere is constantly heated and the other is not? The atmosphere tries to move heat around. Winds form. Jet streams may develop. Hot gas from the dayside flows toward the night side. Cooler gas may return toward the dayside. Chemical species appear and disappear depending on where the gas travels. Iron vapour is carried into darkness and condenses. Other atoms and molecules may behave differently, depending on their own condensation temperatures and how they interact with radiation. The atmosphere becomes a moving chemistry lab, wrapped around a planet. This also shows why average temperature can be misleading. If someone tells you a planet's average temperature, that number can be useful, but it does not tell you the whole weather story. On WASP-76b, the difference between day and night matters more than a single average. Iron may be vapour on one side and condensed on the other. The same planet can hold very different conditions at the same time. On Earth, an average global temperature would not tell you whether it is snowing in one country and hot in another. You need maps, winds, humidity, pressure, and seasons. On WASP-76b, scientists also need a map, though it is a map built from spectra, models, and careful observation, rather than from satellites taking familiar cloud pictures. The iron rain also tells us that alien weather can be chemical in a very visible way. Earth's weather is chemical too, but we often do not think of it that way because water is so familiar. Evaporation, condensation, freezing, melting, cloud formation, and rain are all physical and chemical processes. We experience them as daily life. On WASP-76b, because the material is iron, the chemistry becomes impossible to ignore. The sky is not just moving air, it is a place where metal changes state. That makes the planet feel strange, but it also helps us recognize the same kinds of processes in a new form. Another lesson is that exoplanet weather can be three-dimensional. It is not enough to say that the dayside is hot and the nightside is cooler. The atmosphere has height. Temperature changes with altitude. Winds may blow in different directions at different levels. Some materials may condense high up, while others stay gaseous deeper down. Iron might rain out of the upper atmosphere and then encounter different temperatures below. It might settle, mix, evaporate again, or become part of deeper circulation. The word rain gives us a useful image, but the real process may involve layers, turbulence, cloud formation, and chemical recycling. A weather system is never only a surface event, especially on a gas giant where there may be no surface in the ordinary sense at all. This makes WASP-76b especially different from Earth. Here, rain often falls onto land or ocean. It splashes, flows into streams, seeps into soil, or returns to the sea. On a gas giant, there is no solid ground waiting underneath in the way we understand it. Falling iron condensates would move into deeper layers of gas, into regions of higher pressure and temperature. What happens next depends on the planet's internal structure and atmospheric mixing. The rain may not collect in puddles. It may disappear into the depths. It may become part of a cycle we can only partially infer. That is another reminder that familiar words need careful handling. Rain does not always mean puddles. Clouds do not always mean water. A nightside does not always mean cold. The iron rain also reveals something about how worlds can separate their ingredients. On a planet like WASP-76b, condensation removes certain species from the upper atmosphere in some regions. This is sometimes called rainout. When a vapor condenses and falls deeper, it changes the composition of the air above. That matters for what astronomers observe. If a material rains out on the night side, then the atmosphere returning to the day side may be depleted in that material at the heights we can see. The weather changes the spectrum tells us about the weather. It is a loop of evidence and interpretation. That is why the phrase, "it rains iron," should not make us imagine one isolated storm. It is more like a planetary scale process. The star heats the dayside enough for iron vapor, atmospheric winds transport that vapor, cooler conditions on the night side allow condensation, the upper atmosphere loses some iron. Observations during transit reveal the difference. This is climate, circulation, and chemistry working together. It is not a single cloud having a bad afternoon. It is the atmosphere of a whole giant planet responding to its orbit. The broader field of alien weather is full of examples that stretch our expectations. Some hot Jupiters may have winds moving at several kilometers per second. Some exoplanets may have clouds made of silicate particles, meaning clouds more like rock dust than water droplets. Some cooler worlds may have hazes created by photochemistry, where sunlight breaks molecules apart and lets new compounds form. Titan has methane weather in the cold outer solar system. Venus has clouds of sulfuric acid and a dense atmosphere that traps heat brutally. Jupiter has storms that can last for centuries. Neptune has high-speed winds under faint sunlight. Even inside our solar system, weather is already more varied than a simple Earth-based picture would suggest. Exoplanets only widen the range. WASP-76b sits at the extreme hot end of that range, and that extremity is useful. In ordinary conditions, many processes are subtle. In extreme conditions, they become easier to notice. Iron rain is not subtle. It points clearly to a strong day-night contrast and high-temperature condensation chemistry. It gives scientists a way to test how well their models handle ultra-hot atmospheres. If a model predicts iron should remain gaseous everywhere, but observations suggest it disappears after crossing the night side, the model needs adjustment. If a model predicts the right asymmetry, that is a sign it may be capturing the important physics. Extreme planets help reveal the rules because they push those rules hard. There is also a practical side to studying such weather. The same techniques used to study WASP-76b can be applied to many other exoplanets. Transmission spectroscopy, emission spectroscopy, phase curves, high-resolution Doppler measurements, and atmospheric retrieval models are all tools that help scientists turn faint light into information. Today, those tools reveal iron vapor, sodium, water, carbon monoxide, or strange day-night chemistry on hot giants. In the future, similar methods may help study smaller, cooler planets in more detail. Understanding extreme atmospheres helps sharpen the methods used for all atmospheres. The planet where it rains iron may indirectly help us learn how to read the skies of worlds that are far more Earth-like. This is one reason the study of WASP-76b is not merely a collection of oddities. It belongs to a bigger effort to understand planets as planets, not just as points in orbit. For a long time, finding an exoplanet was the main achievement. Now, astronomers increasingly want to know what those planets are like. What is in their atmospheres? How hot are their daysides? Do they have clouds? Do winds carry heat around? Are molecules present, or are they broken apart by radiation? Does chemistry vary from one side to another? These questions turn detection into characterization. A planet goes from it exists to it has weather, and weather gives a planet personality. That may not be a scientific term, but it is a useful human one. Mars feels different from Venus because their atmospheres and climates are different. Jupiter feels different from Saturn because their storms, bands, and internal heat are different. Titan feels different from Europa because Titan has a thick atmosphere and methane lakes, while Europa has an ice shell and likely an ocean beneath. WASP-76b feels different because its atmosphere can carry vaporized metal into darkness. Weather is one of the ways a world becomes specific. It is how a planet behaves, not just where it is. The iron rain also reminds us that habitability is not the only reason to study atmospheres. It is natural for people to ask whether a planet could support life. That is a wonderful question, and one of the great questions in science. But most planets are not habitable in any Earth-like sense, and they are still worth understanding. WASP-76b is not a candidate for life as we know it. It is too hot, too gaseous, too close to its star, and far too extreme. But it teaches us how atmospheres work under intense stellar heating. It teaches us about planetary migration, tidal locking, chemistry, and observation. A planet does not have to be gentle to be important. In fact, hostile worlds are often excellent teachers. Venus teaches us about runaway greenhouse heating and dense atmospheres. Jupiter teaches us about giant planet storms and deep atmospheric bands. Io teaches us about tidal heating and volcanic activity. Titan teaches us that weather cycles can use methane instead of water. WASP-76b teaches us that metal can become part of an atmospheric cycle when a giant planet is pushed close enough to a star. Each world stretches the definition of what planets can do. Together they prevent us from assuming that Earth is the template for everything. That is a helpful humility. Earth is our home, and because it is our home, it feels normal. But normal is not the same as universal. Our blue sky is not the default sky. Our rain is not the default rain. Our year is not the default year. Our day-night cycle is not the default rhythm. The universe can make planets with years shorter than weekends, skies hot enough for iron vapor, nights where metal condenses, and winds that connect the two halves of a locked world. It can also make frozen moons with methane weather, desert planets, ocean worlds, super-Earths, mini-Neptunes, lava planets, and gas giants larger than anything in our solar system. WASP-76b is one page in a much larger weather atlas. For the listener lying quietly on Earth, this may make the sound of ordinary rain feel a little different. A raindrop against your window is not just a small event. It is part of a planetary system that happens to suit us. Water evaporated somewhere, travelled through air, condensed into a cloud, grew into a droplet, and fell under gravity. On WASP-76b, a very different cycle may happen with iron. On Titan, methane can play a similar role in a much colder world. The universe repeats the pattern with different materials. It changes the temperature, pressure, gravity, and chemistry, then lets weather emerge. There is something calming about that pattern, even when the example is extreme. The universe is varied but not lawless. It does not make iron rain by breaking physics. It makes iron rain by following physics under conditions we do not live in. Heat, condensation, wind, gravity, and light all do their work. That means we can understand it. We can build models. We can test them. We can improve them. A world that first sounds like fantasy becomes a scientific case study, and then a doorway into a wider understanding of planetary climates. WASP-76b also asks us to be precise with imagination. It is fine to imagine iron rain falling through darkness, because that image captures the central idea. But we should also remember the details behind it. The rain may be condensation in the upper atmosphere rather than a neat shower onto a surface. The particles may fall into deeper gas layers rather than onto land. The process may vary by altitude and location. The planet's atmosphere may be more turbulent and layered than the simple phrase suggests. Good imagination does not ignore the science. It lets the science make the picture richer. As our understanding improves, the story of WASP-76b may become more detailed. Scientists may find new chemical signatures, better wind measurements, clearer temperature maps, or evidence for clouds that complicate the original picture. That is not a problem. Science is allowed to refine its own stories. The phrase, iron rain, may remain the doorway, but behind it there will be more rooms, atmospheric circulation, magnetic drag, cloud microphysics, thermal inversions, limb asymmetries, and high-resolution spectroscopy. The planet will not become less wonderful because we understand it better. Usually the opposite happens. The closer we look, the more specific the wonder becomes. By now, WASP-76b has done more than surprise us. It has widened the meaning of weather. It has shown that rain can be a clue to chemistry, that wind can carry metals, that day and night can be places rather than times, and that an atmosphere can be studied even when the planet itself is far beyond reach. It has turned a tiny dip in starlight and a set of spectral lines into an alien climate, and it leaves us with the next careful question. If astronomers can learn this much from a world they cannot visit, how exactly do they do it? How can a planet so distant, so close to its star, and so hidden in glare reveal its atmosphere at all? A planet hundreds of light years away cannot hand us a jar of its air. It cannot send a postcard from the nightside, or a sound recording of metal rain falling into deeper layers of gas, or a little label that says, "Here is what my weather is doing today." WASP-76b is far beyond the reach of any spacecraft we can build, and even if we could cross that distance, the planet itself would not welcome a visitor. There is no safe surface to stand on, no calm cloud deck to float through, no place where a probe could casually open a sample tube and take in a breath of the atmosphere. And yet, somehow, astronomers know that iron is involved in its weather. They know the planet is huge, close to its star, intensely heated, likely locked into permanent day and night, and wrapped in an atmosphere that leaves chemical clues in starlight. That may be one of the most quietly astonishing parts of the whole story. We cannot visit WASP-76b, but we can still learn from it. The key is light. Not light as a vague glow in the sky, but light as a carrier of information. Every star sends out radiation across many wavelengths, and that light travels through space for years, decades, centuries, or longer. Most of the time, when we look at a distant star, we're seeing the star itself. But if a planet passes in front of that star from our point of view, something delicate happens. A small portion of the starlight is blocked by the planet's dark disk, and an even smaller portion slips through the planet's atmosphere before continuing toward Earth. That thin ring of atmosphere changes the light very slightly. It removes certain colours. It leaves fingerprints, and if our instruments are sensitive enough, those fingerprints can tell us what the planet's atmosphere contains. This method is called transmission spectroscopy, which sounds like something that might require a lab coat and a very serious expression, but the basic idea is gentle enough. Imagine sunlight passing through stained glass. The glass changes the light before it reaches your eyes. Or imagine looking at a sunset through Earth's atmosphere, where air, dust and molecules scatter the shorter blue wavelengths and leave the sky glowing red and orange. The atmosphere has filtered the light. Around an exoplanet, the filtering is far more subtle, and the planet is much farther away, but the principle is similar. Starlight passes through gas. The gas absorbs certain wavelengths. Those missing wavelengths reveal the gas. Every atom and molecule interacts with light in its own particular way. Sodium, iron, water vapor, carbon monoxide, hydrogen, helium, and many other species can each leave recognizable patterns in a spectrum. A spectrum is what you get when light is separated into its colors or wavelengths, much like a rainbow, but measured with far greater precision. If white light is like a full piano chord, a spectrum lets scientists hear which notes are missing. Those missing notes can identify the material that absorbed them. This is why astronomers often say that light carries fingerprints. The atmosphere does not need to be touched, it only needs to leave its mark. For WASP-76b, those marks are tiny compared with the overwhelming brightness of the star. The planet is much dimmer than the star, and the atmosphere is only a thin rim around the planet during transit. Trying to study it is a little like trying to hear someone whisper from across a busy train station while a brass band rehearses nearby. The star dominates everything. The planet's atmospheric signal is small, hidden and delicate, but with powerful telescopes, stable spectrographs, careful timing, and a great deal of analysis, that whisper can be separated from the noise. One of the instruments used to study WASP-76b is Espresso, attached to the Very Large Telescope in Chile. The name is cheerful, almost cozy, though the instrument itself is one of the most precise spectrographs in the world, rather than something you would find beside a sleepy kitchen mug. Espresso separates light into extremely fine detail, allowing astronomers to look for tiny spectral features and tiny Doppler shifts. It was built for high-precision work, including the study of exoplanets. For a planet like WASP-76b, that precision is exactly what is needed. The signal is faint, the star is bright, and the atmosphere is moving. A rough instrument would miss the story. A precise one can begin to read it. During a transit, WASP-76b crosses the face of its star. From Earth, the star dims slightly because the planet blocks part of the light. That dimming tells astronomers the planet's size relative to the star. A larger planet blocks more light, a smaller planet blocks less. Repeated transits reveal the orbital period, which for WASP-76b is only about 1.8 Earth days. The regular rhythm tells us the planet is racing around its star in a very tight orbit. But the transit does more than reveal size and timing. It also creates the chance to study the atmosphere, because some of the starlight passes through the atmospheric edge before it reaches us. Think of the planet's atmosphere during transit as a thin glowing outline, though not glowing in the visible sense from our point of view, but outlined by the starlight passing through it. The solid part of the planet blocks light completely. The atmosphere lets some light through, but not all wavelengths equally. If iron vapor is present in the upper atmosphere, it absorbs at iron's characteristic wavelengths. If sodium is present, sodium leaves its own signs. If molecules are present, they can leave broader or more complex patterns. The telescope gathers the light. The spectrograph spreads it out. Scientists compare what they see during transit with what they see when the planet is not in front of the star. The difference can reveal the atmosphere. Of course, the difference is incredibly small. Earth's own atmosphere also absorbs light. The telescope and instrument add their own effects. The star itself has spectral lines and surface variations. The planet is moving quickly around the star. The star may be moving slightly too, pulled by the planet's gravity. Everything is shifting, blending and changing at once. So astronomers have to carefully remove the signals they do not want in order to isolate the planet's atmosphere. This is not glamorous in the cinematic sense. It involves calibration, correction, modelling, and a lot of patient checking. But this quiet work is what turns a faint pattern into a reliable conclusion. Doppler shifts add another layer of information. When gas moves toward us, the light it absorbs or emits is shifted slightly towards shorter wavelengths. When gas moves away, the shift goes the other way. This is similar to the change in pitch you hear when an ambulance passes, though with light instead of sound. On WASP-76b, the atmosphere is moving because the planet orbits, rotates, and has strong winds. As the planet crosses the star, different parts of its atmosphere move at different velocities relative to us. By measuring shifts in the spectral lines, astronomers can infer motion. The atmosphere is not just identified by what it contains, but by how it moves. That matters deeply for WASP-76b because the iron rain story depends on atmospheric circulation. The planet has a permanent dayside and a permanent nightside. Iron vapor can exist on the intensely heated dayside. Winds carry that vapor toward the cooler nightside. There, it may condense and fall out of the upper atmosphere. When scientists detect iron strongly in one part of the planet's limb and not in another, they are not just making a chemical inventory, they are seeing evidence that the atmosphere changes around the planet. Chemistry and motion are linked. The spectrum becomes a weather map, though a very unusual one. The two limbs of the planet are especially important. During transit, astronomers can distinguish, with advanced analysis, between the region where air is moving from the dayside toward the nightside, and the region where air has crossed through night and is returning toward day. These regions are often described as the evening and morning limbs. They are not evening and morning in the Earth sense, with a sunrise or sunset moving across the ground. On a tidally locked planet, they are more like permanent transition zones. Still, the names help us understand the flow. One side is receiving air fresh from the hot dayside. The other has air that has passed through darkness. If iron has condensed on the night side, the returning air may show less iron vapor. That difference can be observed as an asymmetry in the spectral signal. This is an extraordinary idea when you pause with it. From Earth, astronomers can detect not only that a distant planet has an atmosphere, and not only that the atmosphere contains iron, but that the iron may be distributed differently from one side of the planet's limb to the other. That means we're no longer treating the planet as a simple dot with one average temperature and one average composition. We're beginning to see its atmosphere as a place with regions, flows, and changing chemistry. It is not a full map, not yet, but it is a step toward mapping weather on a world we cannot see directly. Another method helps too, observing the planet at different phases of its orbit. When WASP-76b is in front of the star, we study transmission through the atmosphere. When it moves behind the star, the planet's light is briefly hidden. Just before and after that secondary eclipse, astronomers can compare the combined light of star and planet with the star alone. This can reveal something about the planet's dayside emission, the heat glowing from the star-facing hemisphere. The star is still overwhelmingly brighter, but the difference contains information. In some cases, scientists can study how brightness changes through the orbit, building what is called a phase curve. A phase curve can show whether the hottest region is shifted by winds, whether the night side emits much heat, and how efficiently the atmosphere moves energy around. WASP-76b has also been studied using high-resolution emission and retrieval techniques, where researchers try to pull out the planet's own spectral signal from the stellar glare. Retrieval is a word scientists use for the process of inferring atmospheric properties from observed spectra. It is a bit like solving a puzzle backward. You start with the light you received, then ask what temperature structure, chemistry, winds and abundances would produce that light. There is no single magic answer at first. Models are tested. Assumptions are adjusted. Different possibilities are compared. The best explanations are the ones that match the data while remaining physically reasonable. It is slow, careful work, but it is how a distant atmosphere becomes a set of measurable properties. The atmosphere of WASP-76b reveals more than iron. Different studies have explored other species such as sodium, calcium, magnesium, vanadium oxide, and additional high-temperature signatures, depending on the wavelength range and instrument used. Each detection or non-detection adds another piece to the picture. Some species may trace hotter regions, others cooler regions. Some may survive on one side and vanish on another. Some may be affected by clouds or condensation. The atmosphere is not a simple list of ingredients like a recipe on the back of a packet. It is a changing environment, and the ingredients appear differently depending on altitude, temperature, and motion. This is why scientists often combine observations with atmospheric models. The data alone gives clues, but the models help connect those clues into a physical story. A model can simulate how radiation from the star heats the dayside, how winds flow from day to night, how temperature changes with pressure, and where iron should condense. Then researchers compare the model with the observed spectra. If the model predicts iron vapor on both limbs, but observations show it missing from one, something must be adjusted. Maybe condensation is stronger, maybe winds are different, maybe clouds or vertical mixing matter. The planet becomes a test for the model, and the model becomes a tool for interpreting the planet. There is a wonderful humility in this process. Astronomers are not simply declaring what WASP-76b is like after one observation. They gather evidence, compare methods, repeat measurements, and refine the picture. Some results confirm earlier interpretations, others complicate them. Follow-up work can reveal that the atmosphere varies over time, or that different species behave differently, or that the original picture needs more nuance. That is not a weakness. It is how science becomes stronger. A simple phrase like iron rain opens the door, and then the details continue to grow behind it. One of the details that matters is altitude. When starlight passes through the atmosphere during transit, it does not sample every layer equally. It mainly tells us about the upper atmosphere at the pressures where the gas becomes transparent enough for light to pass through, but dense enough to absorb measurable wavelengths. Deeper layers may be hidden. This means that when astronomers say iron is condensing out of the observable atmosphere, they are often talking about the layers accessible to their instruments. The planet may have deeper processes we cannot directly see. The atmosphere is like an ocean of gas, and our view often skims its upper regions. Pressure also changes the story. At low pressure high in the atmosphere, atoms and molecules interact with light in certain ways. Deeper down, higher pressure can broaden spectral lines, change chemistry, and affect condensation. Temperature does not have one value for the whole planet. It changes with height and location. So an atmospheric model must consider pressure and temperature together. A substance that is vapor at one level may condense at another. A species visible in one spectral line may be hidden in another region. Reading an exoplanet atmosphere is not like reading a simple label. It is like reading a layered book through a keyhole while the book is moving. The star itself is part of the challenge. WASP-76b orbits very close to a bright F-type star, and the star's light is both the tool and the obstacle. Without the star, there would be no strong backlight during transit. With the star, the planet is drowned in glare. The same light that reveals the atmosphere also hides it by being so much brighter. This is a common theme in exoplanet science. Stars are generous and inconvenient at the same time. They illuminate their planets, shape their climates, and provide the light we analyze, but they also make those planets difficult to detect. It is rather like trying to study a firefly fluttering next to a lighthouse. Because WASP-76b transits often, astronomers can observe multiple events. That repetition is valuable. One transit may be affected by weather on Earth, instrument conditions, or noise. Multiple transits allow scientists to compare results and strengthen confidence. If the same kind of signal appears again, it becomes more convincing. If it changes, that may reveal atmospheric variability or observational challenges. WASP-76b's short orbit makes it a useful target because it offers frequent opportunities. The planet keeps crossing its star, and each crossing is another chance to read the thin ring of its sky. There is also the matter of scale. The signals astronomers search for are tiny, but the physical systems behind them are enormous. A slight shift in a line may represent winds moving across a giant planet. A small absorption feature may reveal metal vapor in an atmosphere larger than Jupiter's. A missing signal may imply condensation across a whole night hemisphere. This is one of the strange beauties of astronomy. Small measurements can point to gigantic realities. A few photons, properly understood, can tell the story of a world. If this feels almost impossible, that is understandable. It is one thing to say that light contains information. It is another to believe that enough information survives the journey across space, through Earth's atmosphere into a telescope, through an instrument, and into a computer, to reveal weather on a planet we cannot visit. But this is exactly what modern astronomy has become very good at. It does not always need images. It can work with timing, brightness, colour, motion, and missing light. It can infer the unseen from the measurable. That skill has opened the exoplanet era. Not long ago, the planets of other stars were mostly speculation. Now thousands are known, and a growing number have atmospheres being studied. Some are hot Jupiters like WASP-76b, some are smaller, some orbit red dwarfs, some are puffy, some dense, some scorching, some cold. For many of them, we know only basic facts. For a few, the atmosphere is beginning to come into view. WASP-76. B belongs to that group of worlds whose skies are not just guessed at, but investigated. We know it through the way it changes starlight. This is why instruments like espresso, harps, and future spectrographs are so important. They are not just machines that make sharper graphs. They are bridges between Earth and distant atmospheres. They turn light into chemistry. They turn motion into wind. They turn tiny dips into planetary orbits. They turn a star's spectrum into a weather report from a place no human body could survive. And as telescopes become larger and instruments more sensitive, those bridges will become stronger. We may study more exoplanets in greater detail, perhaps even smaller worlds where the question is not iron rain, but water vapour, clouds, surface pressure, and the possible signs of life. WASP-76b is not that kind of gentle target. It is not a second Earth. It is not a place where biology seems likely in any familiar form. But it is an excellent teacher of method. It shows how astronomers can go from a transit to an atmosphere, from a spectrum to a chemical species, from a Doppler shift to winds, from limb asymmetry to day-night climate. It shows that even hostile worlds can be understood with patience, and it reminds us that studying exoplanets is not only about finding another home, it is about learning what planets can be. Perhaps the most comforting part is that the whole investigation begins with careful noticing. A star dims a little. Light is spread into colours. A line appears where iron should be. A line shifts slightly because gas is moving. A signal is stronger on one side than another. None of these details shout. they whisper. Yet together they tell us about a giant planet locked to its star, about winds carrying metal, about a nightside where vapor cools and falls. The universe often speaks very softly, and science is the art of learning how to listen. So when we imagine WASP-76b now, we can imagine it with more than drama. We can imagine the method behind the drama, the transits repeating every 1.8 days, the starlight passing through the atmospheric rim, the spectrograph separating colours with extraordinary care, the iron lines appearing and shifting, the models trying to match the movement of gas from day to night. The human patience required to turn a faint signal into a picture of alien weather. A planet we cannot visit becomes, in this way, a planet we can still know. And once a planet can be known through starlight, even faintly, it stops being just a distant point in a catalogue. It becomes part of a larger map of planetary possibility. WASP-76b tells us that giant worlds can be roasted into strange chemistry, that atmospheres can carry metals like weather ingredients, and that the border between day and night can be written into a spectrum. Far from being only a spectacular oddity, WASP-76b is a lesson in how many kinds of planets the universe can make when it is not trying to make another Earth. It would be easy to leave this world as a single strange image, a giant planet too close to its star, with iron vapour rising in the heat and metal rain falling in the dark. That image is unforgettable, and it deserves to be. But if we stay with it a little longer, if we let the picture settle and ask what it means, WASP-76b becomes more than the planet where it rains iron. It becomes a window into the wider family of extreme worlds beyond our solar system, places where the rules we know still apply, but the conditions are so different that the results feel almost unreal. For most of human history, the word planet meant the few wandering lights visible in our sky. Mercury, Venus, Mars, Jupiter and Saturn were known long before telescopes because they moved against the background stars. Later, Uranus and Neptune joined the family, then many smaller bodies, moons, asteroids, comets, and dwarf planets. Our solar system became the example we had, the classroom model on the desk. Close to the sun, small rocky planets. Farther out, giant worlds of gas and ice. Beyond them, frozen leftovers and distant objects moving slowly in the dark. It was tidy enough to make us think, perhaps without realizing it, that planetary systems were supposed to look something like ours. Then exoplanets began to appear in the data, and the tidy picture became much more interesting. Astronomers found giant planets orbiting scorchingly close to their stars. They found worlds larger than Earth, but smaller than Neptune, a category our own solar system does not contain. They found planets moving around two stars, planets on strange orbits, planets so light and puffy they seem almost swollen, planets so dense they may be rich in heavy elements, and planets so hot that their atmospheres glow and their molecules break apart. The galaxy did not simply repeat our solar system again and again. It built with variety. It experimented with distance, mass, heat, chemistry, and time. WASP-76b belongs to that larger surprise. This planet teaches us first that location can completely transform a world. A gas giant like Jupiter, placed far from its star, becomes a cold, banded planet with deep storms and ammonia clouds. A gas giant moved very close to its star becomes something else. It becomes inflated by heat, blasted by radiation, possibly tidally locked and forced into an extreme day-night climate. WASP-76b is not strange because it is made from impossible ingredients. It is strange because familiar ingredients are placed in unfamiliar conditions. Hydrogen, helium, metals, heat, gravity, and starlight come together in a way our solar system does not show us. The same physics that gives Jupiter its storms helps give WASP-76b its metal weather. Once the distance to the star is changed, that is a useful idea far beyond this one planet. Worlds are not defined only by what they are made of. They are also defined by where they are, what kind of star they orbit, how fast they move, how strongly they are heated, whether they rotate freely or become locked, and how their atmospheres respond. Earth would not be Earth if it orbited where Mercury does. Jupiter would not be Jupiter if it circled the Sun every 2 days. A planet's identity is not just a list of ingredients, it is a relationship with its star. WASP-76b also teaches us that atmospheres can be much more varied than the weather we know. On Earth, weather is mostly a water story. Water evaporates from oceans, condenses into clouds, falls as rain or snow, freezes, melts, flows, and rises again. That cycle shapes landscapes, feeds ecosystems, and gives rainy nights their soft, familiar sound. But in the wider universe, water is not always the main actor. On some worlds, methane can rain. On others, mineral clouds may form. On ultra-hot planets, metals and other high-temperature materials can become visible parts of the atmosphere. Weather is not a substance, weather is movement, energy, pressure, condensation and change. WASP-76b stretches the definition until iron itself becomes part of the sky. This matters because it keeps us from using Earth as the only measuring stick. Earth is our home, but it is not the universe's default planet. Our air, oceans, clouds and seasons feel normal because we evolved inside them. A world with permanent day and night feels strange to us because our bodies expect sunrise and sunset. A world where iron reigns feels impossible because iron is solid in our daily lives. But nature is not asking what feels normal to a human hand or a human clock. It is following conditions. Raise the temperature high enough and iron can vaporize. Move that vapor into cooler air and it can condense. Put the whole system on a tidally locked gas giant and the result becomes alien weather. Another lesson is that extreme worlds help scientists test the limits of their models. A mild planet can hide some of its processes because everything happens within a familiar range. An extreme planet exaggerates the physics. WASP-76b is intensely heated, rapidly orbiting, probably locked to its star, and large enough for its atmosphere to leave clear signals during transit. That makes it a powerful target. Scientists can ask whether their models correctly predict day-night temperature differences, wind speeds, condensation, chemical gradients, and spectral signatures. If the model fails, the planet points to what needs improvement. If the model works, scientists gain confidence that they understand part of the machinery of planetary atmospheres. In this sense, WASP-76b is like a stress test for planetary science. Engineers test materials under high pressure or high heat to see how they behave at the edge. Astronomers study ultra-hot Jupiters to see how atmospheres behave, when starlight, radiation and wind push them far beyond anything we see on Earth. The planet is not comfortable, but it is useful. It shows what happens when a gas giant is placed under extreme stellar forcing. It shows how chemistry can vary across a single planet. It shows that weather can remove certain elements from the upper atmosphere in some regions and leave them visible in others. It turns a world into a laboratory. WASP-76 also teaches us that planets are not simple. A distant world might begin as a few numbers in a catalogue: mass, radius, orbital period, distance from star. Those numbers are important, but they are only the outline. Once astronomers study the atmosphere, the planet becomes more detailed. The dayside is different from the nightside. The evening limb is different from the morning limb. The upper atmosphere may move differently from deeper layers. Iron may trace one kind of behaviour while sodium, calcium, magnesium, or other species trace another. The planet is not a uniform ball. It has structure, it has regions, it has motion, it has a climate, even if that climate is completely hostile. That is a major shift in how we understand exoplanets. Finding a planet is no longer the final step. It is the beginning. First we detect it, then we measure its orbit, then its size and mass. Then, if we are fortunate and the planet is well placed for observation, we begin to ask what its atmosphere contains. We look for light filtered through its sky. We search for missing colours. We measure Doppler shifts. We compare transits. We build models and test them. The planet slowly becomes a place in our scientific imagination. Not a place we can visit, but a place with enough character to study. There is something deeply impressive about learning this much from starlight. WASP-76b does not appear to us as a detailed image. It does not show us clouds swirling across a visible disk. Most of what we know comes from indirect clues. A star dimming, spectral lines shifting, iron appearing in one part of the atmosphere and not another. Yet those clues are enough to reveal a giant planet where the dayside can vaporize metal and the nightside can condense it. This tells us something about the power of modern astronomy. We have reached a point where the atmosphere of a planet hundreds of light years away can become a measurable subject. And this is only the beginning. Instruments are improving, telescopes are becoming more powerful, analysis methods are becoming more refined. The same techniques used to study extreme hot Jupiters today may help study smaller and cooler planets in the future. WASP-76b is not habitable, but learning to read its atmosphere helps scientists practice the art of reading atmospheres in general. One day, the same broad approach may help reveal whether a rocky planet around another star has water vapor, carbon dioxide, oxygen, methane, clouds, or other signs that tell us about its environment. A world of iron rain may help sharpen the tools that eventually study worlds much gentler than itself. That is one of the quiet connections between the extreme and the familiar. We do not study WASP-76b because we expect to live there. We study it because it teaches us how planets work. It teaches us how atmospheres respond to heat. It teaches us how radiation changes chemistry. It teaches us how winds move energy around locked worlds. It teaches us how to turn tiny signals into physical understanding. A planet does not have to look like Earth to help us understand Earth-like planets. Sometimes the most hostile worlds make the best teachers because their processes are loud enough, bright enough, and strange enough to detect. This planet also teaches us that our solar system is only one small sample. We have 8 major planets here, each wonderful in its own way, but 8 is not enough to describe what planets can be. If all we knew were our own worlds, we might think giant planets usually live far from their stars. Hot Jupiters change that. We might think weather usually belongs to water, methane, ammonia, or familiar gases. Ultra-hot planets change that. We might think day and night are always cycles. Tidally locked worlds change that. Again and again, exoplanets have warned us not to confuse local experience with universal law. WASP-76b sits in a category that would have seemed wildly unexpected before exoplanet discoveries became common. A Jupiter-sized world orbiting in less than 2 days, swollen by heat, locked to its star, with a dayside hot enough for metal vapor. If someone had described it before such planets were known, it might have sounded more like fiction than astronomy. But the discovery of exoplanets has repeatedly shown that reality is comfortable being stranger than our first guesses. The universe has had billions of years and countless stars to build planetary systems. It has more patience than we do, and a much larger workshop. This variety also changes how we think about home. Earth is not special because it is the only kind of planet possible. Earth is special because among the enormous range of possible worlds, it has the right combination of distance, atmosphere, water, geology, magnetic history, and time to support the life we know. WASP-76b makes Earth feel delicate by comparison. Our rain is water, not iron. Our nights are temporary, not eternal. Our winds can be violent, but they do not carry vaporized metal around a giant planet. Our sun warms us from a safe distance. Our atmosphere is thin, breathable, and balanced enough for oceans and forests. The more extreme worlds we study, the more remarkable ordinary Earth becomes. There is no need to turn that into fear. It can simply become appreciation. A rainy evening here is not boring. It is a sign of a planet with surface water, moderate temperatures, atmospheric circulation, and gravity working together in a way that suits life. A cloud over your town is part of a system as real and physical as the metal weather of WASP-76b, only gentler. When we compare the two, Earth does not become less interesting. It becomes more specific. It becomes one outcome among many, and a precious one. WASP-76b also reminds us that extreme planets can be beautiful in the scientific sense, even when they are deadly in every practical sense. Beauty in science is not always softness. Sometimes it's clarity. Sometimes it is the way one observation explains a chain of processes. Iron vapor on the dayside, winds crossing the terminator, condensation on the nightside. Asymmetric absorption in starlight. Each piece fits into a larger pattern. There is beauty in that pattern, not because the planet is gentle, but because it is understandable. The phrase, planet where it rains iron, may be what brings people to the story, but the deeper wonder is that we can explain why. It is not a random miracle. It is not a fantasy spell. It is a chain of cause and effect. The orbit is tight, so the star's heat is intense. The planet is likely tidally locked, so one side is always hot and one side is cooler. Iron vapor survives in the furnace. Winds carry it into darkness. Cooler temperatures allow condensation. Light passing through the atmosphere reveals the difference. The strange image becomes a scientific result. That is the kind of wonder that lasts. A simple surprise may fade after a moment, but a surprise with an explanation keeps opening. Once you understand iron rain, you begin to ask about other species. If iron condenses, what about magnesium, calcium, chromium, or titanium? If the dayside breaks molecules apart, what reforms on the nightside? If winds carry metal, how fast do they move? If the atmosphere has layers, which layers are we seeing? If one ultra-hot Jupiter behaves this way, do others behave similarly, or does each have its own chemistry and circulation? One answer becomes several questions. That is usually a sign that science is alive. There are still many uncertainties. Scientists continue to refine models of WASP-76b's atmosphere. The details of its winds, temperature structure, clouds, and chemical gradients are not all settled. Observations from different instruments and methods may add nuance. Future telescopes may reveal more about the dayside, the nightside, and the substances moving between them. This is important to say because good science does not freeze a planet into one sentence forever. It allows the picture to improve. WASP-76b is famous for iron rain, but it is also an active research target. And active research means the story still has edges that are being filled in. That uncertainty does not weaken the planet's importance. It makes it more interesting. A fully solved world would be a museum object. WASP-76b is more like an ongoing conversation between observation and theory. The planet offers signals. Scientists interpret them. Models are tested. New observations challenge or support those interpretations. The picture becomes sharper. This is how distant worlds enter human knowledge, not all at once, but gradually through repeated attention. For the wider search for planets, WASP-76b stands as one example of how diverse atmospheres can be. Some worlds may be clear on one side and cloudy on the other. Some may have strong chemical gradients. Some may lose atmosphere to space. Some may glow strongly in infrared light. Some may have molecules destroyed by ultraviolet radiation and rebuilt elsewhere by winds. These are not small details. Atmospheres control what we can observe, how planets evolve, and whether any world might be habitable. Understanding extreme atmospheres helps build the larger framework needed to interpret all planets. And so, as we let the image of WASP-76b slowly drift back into the dark, it leaves us with a bigger view of the galaxy. Around other stars, planets are not rare decorations. They are common and varied. Some are quiet, some are violent, some are frozen. Some are swollen, some may have oceans, some may have lava skies, some orbit far away in long cold years, while others rush around their stars in only a day or two. WASP-76b is one of the extreme ones, a giant world living too close to its star for anything like calm, but perfect for teaching us what heat can do to a planet. Perhaps that is the most important lesson. The universe is not only filled with objects, it is filled with conditions. Change the conditions and matter behaves differently. Put water at Earth temperatures and it rains from clouds. Put methane in Titan's cold and it can gather into lakes. Put iron in the atmosphere of an ultra-hot giant and it can become vapour, travel with winds and fall in the dark. The same laws of physics run through all of it. The variety comes from where the worlds are placed, how they move, what they are made of, and how long they have had to change. So tonight, we have travelled from a small dimming of starlight to a giant world of permanent day and night. We have followed iron from the star-facing furnace into the cooler darkness. We have watched, in thought, as winds carried metal around a planet we cannot visit. We have seen how a spectrum can become a weather report, and how a strange exoplanet can teach us about the wider possibilities of planetary science. And through it all, Earth has remained quietly beneath us, with its water clouds, breathable air, turning days, and rain that can still sound gentle against a window. If this journey has helped your thoughts settle, or if the strange weather of a faraway world has made your own room feel a little calmer, I would be ever so grateful if you liked the video, subscribed, and shared this quiet corner of science with someone else who might enjoy drifting through the universe at a softer pace. WASP-76b is not a place for sleep, not with its iron skies and star-locked furnace, but learning about it can still bring a certain peaceful wonder. It reminds us that the galaxy is wider than our assumptions, that even the harshest worlds can be understood, and that every small point of light may have a story hidden inside it. For now, let the iron rain fall far away, safely beyond our reach, on the dark side of a giant planet circling its star in less than 2 days. Let Earth remain here beneath you, turning slowly through its familiar night. Somewhere outside the weather may be clear, cloudy, windy, or wet. Somewhere above, starlight is still crossing space, carrying messages from worlds we have not yet learned to read. And as your own thoughts begin to slow, you can rest with the simple, steady fact that even in a universe of metal rain and burning skies, there is still room for quiet, curiosity, and sleep.